Hello there and welcome to Science for Sleep, where we take some of the strangest ideas in science, slow them down, make ourselves comfortable, and see if we can understand them without requiring 3 blackboards, 6 cups of coffee, and an advanced degree in theoretical physics. Tonight we're heading toward one of the strangest objects ever suggested by string theory. It's called a fuzzball. And before we go any further, I should probably reassure you that this is a real scientific term. Physicists really do use the word fuzzball, which is slightly unfortunate because if you heard the word without any context, you might imagine something discovered underneath a sofa. Perhaps a collection of dust, cat hair, and several objects you were convinced had disappeared years ago. But in theoretical physics, a fuzzball is something considerably more ambitious. It may be an entirely different way of understanding a black hole, not merely something sitting inside a black hole, not a strange object floating near the centre. The idea is much more radical than that. According to the fuzzball proposal in string theory, what we normally describe as a black hole may actually be made from an enormous number of strings and other objects allowed by string theory, arranged in a complicated quantum state that extends across roughly the region where we expected the black hole to be. In that picture, the familiar black hole with an empty-looking horizon and a mysterious interior may not be the full story. And that is where things become interesting, because black holes already have a reputation for being rather difficult. They are regions where gravity becomes so strong that once something crosses a certain boundary, known as the event horizon, it cannot return to the outside universe according to the usual description of general relativity. Light cannot escape. Matter cannot escape. A badly planned sightseeing trip cannot escape. And somewhere deeper inside the traditional mathematical description, matter appears to collapse toward a singularity, a place where our equations stop behaving sensibly and where quantities such as density and space-time curvature seem to become infinite. For many years this picture was strange enough. Then quantum mechanics arrived at the black hole and made the situation considerably worse. Quantum theory tells us that information about a physical system should not simply disappear. If you know the complete quantum state of something and understand how it evolves, the information contained in that state is preserved. You can scramble it. You can make it extraordinarily difficult to recover. You can turn a neat arrangement into such a complicated mess that no reasonable person would volunteer to reconstruct it before breakfast. But the underlying information is not supposed to vanish. Black holes seem to challenge that principle. In the 1970s, Stephen Hawking showed that black holes should not remain completely black. Quantum effects near them cause what we now call Hawking radiation. Over extremely long periods of time, a black hole can lose energy through this radiation and gradually shrink. Eventually, at least according to the simplest version of the calculation, it can evaporate, and that creates a problem. Imagine throwing something into a black hole. A book, perhaps. We won't choose a particularly valuable book. It seems unfair to destroy a first edition for a thought experiment. The book crosses the horizon, and according to the traditional picture, it falls inward. Much later, the black hole emits Hawking radiation. But the radiation in Hawking's original calculation appears thermal. It doesn't obviously carry the detailed information needed to tell us exactly what fell into the black hole. Then the black hole disappears. The book is gone. The black hole is gone. And the information describing the book appears to be gone as well. Quantum mechanics looks at this situation and says that shouldn't happen. General relativity looks at quantum mechanics and politely refuses to solve the problem. And physicists have spent decades trying to work out what nature is actually doing. This is the black hole information paradox, and it is one of the main reasons fuzzballs entered the conversation. The fuzzball idea grew from attempts to understand black holes using string theory. String theory begins with an unusual suggestion of its own. Instead of treating the most basic ingredients of nature as tiny point-like particles, it describes fundamental objects as extremely small strings. Different vibrational states of those strings can appear to us as different particles. But once physicists began exploring the theory more deeply, the inventory became larger. There are not only strings, there are higher dimensional objects, usually called branes. There are extra dimensions, There are complicated ways these ingredients can wrap around those dimensions. There are charges, vibrations, momentum, topology, quantum states, and enough mathematics to make an ordinary ball of fuzz sound refreshingly straightforward. When researchers used these tools to study certain kinds of black holes, they discovered something remarkable. They could count enormous numbers of microscopic quantum states associated with a black hole. This mattered because black holes have entropy, and entropy in statistical physics is closely connected to the number of microscopic arrangements that can produce the same large-scale appearance. A glass of water, for example, looks simple from across the room. It's just water in a glass. But microscopically, an enormous number of molecules can be arranged in an enormous number of ways while still giving you what looks like exactly the same glass of water. Black holes appear simple from the outside too. Once they settle down, traditional descriptions say that relatively few measurable properties are needed to describe them, such as mass, electric charge, and angular momentum. You could have formed one from a collapsing star. You could have thrown planets into it. You could have added several unfortunate teapots. From far away, much of that detailed history seems hidden. Yet the black hole's entropy suggests there must be an extraordinary number of possible microscopic states underneath that simple exterior description. The obvious question is, what are those states? What actually differs from one black hole microstate to another? String theory offered a possible answer. In certain theoretical examples that physicists have been able to study in detail, the microscopic states are not all identical objects, with information somehow stored at an unreachable central point. Instead, different arrangements of strings and branes can produce different geometries and quantum configurations, and some of those configurations do something that sounds almost rebellious. They avoid producing the ordinary black hole interior altogether. No standard empty region behind a perfectly smooth horizon leading inevitably toward a singularity. Instead, the structure associated with the microstate extends outward. The would-be black hole is replaced by a complicated quantum object. That object is what people began calling a fuzzball. Now, the word fuzz requires a little care. We're not talking about literal fluff. There isn't a cosmic tumble dryer somewhere producing giant balls of string and lint. And if you could somehow fly toward one, which we will strongly advise against for several reasons, you shouldn't expect to see something resembling a giant woolly pom-pom hanging in space. Fuzzball is a way of referring to the highly complicated stringy structure of the state. The important point is that the information is associated with the structure itself. It isn't necessarily hidden behind a conventional horizon in the way the simplest black hole picture would suggest. That changes the information problem dramatically. If the object has physical quantum structure all the way out toward the place where a horizon would normally have formed, then radiation can, in principle, interact with that structure. And if radiation can depend on the details of the structure, information might escape gradually with the radiation. The black hole would no longer need to perform the deeply suspicious trick of swallowing quantum information and deleting it from the universe. Instead, it would behave more like an extraordinarily compact quantum object with an absurd number of possible internal arrangements. That is the attraction of the fuzzball proposal. It attempts to keep quantum mechanics intact by changing what we think a black hole actually is. Of course, there is an important phrase we need to keep nearby throughout tonight's discussion: the fuzzball proposal. Not the fuzzball fact. Not the fuzzball photograph. Not the fuzzball confirmed last Tuesday by someone with a telescope. This is an active idea in theoretical physics. String theorists have constructed important families of microstates, and those results have taught us a great deal about how black hole entropy and quantum structure may work. But researchers do not yet have a complete fuzzball description of every realistic black hole in our universe. There are difficult questions about how general the known constructions are, how collapsing matter would behave, what an observer falling towards such an object would experience, and exactly how the description connects to the smooth space-time predicted by general relativity. So we won't treat fuzzballs as a secret answer that physicists have already discovered and simply forgotten to mention. Science is usually less tidy than that. Instead, we're going to look at why anyone would propose such an unusual object in the first place, what string theory actually contributes to the idea, what physicists mean by a black hole microstate, why horizons and singularities become controversial, and how a fuzzball might allow information to escape. We'll also encounter several things that sound as though they were named during a particularly imaginative afternoon. Strings, brains, microstates, extra dimensions, black hole hair, fuzzball complementarity, and eventually, questions about what someone falling toward a fuzzball might actually encounter. All of that is ahead of us. For the moment, though, I want to ask you something a little easier. Where in the world are you listening from tonight? And while you're there, perhaps look around for a moment and consider the nearest ordinary object. A pillow, a lamp, a cup of tea, a phone you're definitely about to put down in a responsible and sleep-friendly manner. Whatever it is, imagine compressing enough mass into a small enough region that gravity becomes overwhelming. At some point, our everyday understanding of objects stops being useful. There is no obvious surface to stand on in the traditional description of a black hole. There is no convenient label saying interior begins here. There is an event horizon, which is not a material shell, but a boundary in space-time. Cross it, and the routes that could have taken you back outside are gone. That description comes from general relativity, and general relativity has been extraordinarily successful. It predicts how planets move, how light bends around massive objects, how clocks respond to gravity, and how gravitational waves travel across the universe. So the fuzzball proposal isn't motivated by physicists becoming bored with perfectly good black holes and deciding they needed something with a friendlier name. The problem appears when we ask general relativity and quantum mechanics to describe the same black hole all the way through its life. Each theory works remarkably well in its own territory. Together they produce uncomfortable questions, and black holes sit directly in the middle of those questions. They combine gravity, quantum physics, thermodynamics, information, and the basic structure of space-time in one very inconvenient package. You can think of them as nature's most difficult group project. Everyone has turned up. No one agrees on the presentation. String theory is one attempt to provide a framework in which gravity and quantum mechanics can coexist. And when physicists use that framework to examine black holes, they don't merely get a small correction to the old picture. In the fuzzball approach, the correction can become enormous. That is one of the reasons this subject is worth taking slowly. Our usual instinct is to imagine quantum gravity as something important only at incredibly tiny distances, perhaps near the singularity at the very centre of a black hole. From that point of view, you might expect the event horizon to remain completely ordinary. A large black hole can have a horizon where the local curvature of space-time is not especially extreme. An astronaut crossing it, according to classical general relativity, might notice nothing dramatic at that exact location. There would be no wall, no flashing warning sign, no gentleman at a desk asking whether you've completed the appropriate paperwork for entering a one-way region of space-time. You would simply continue inward. The fuzzball idea challenges that expectation. The stringy quantum structure may extend across a region comparable to the size associated with the black hole itself. In other words, quantum gravity might not remain politely hidden near the centre. It may change the entire object, and if that sounds like a very large claim, it is. That's why physicists have spent years testing the idea through specific mathematical examples, rather than merely deciding that fuzzy black hole has a pleasant ring to it. There is another reason the concept is easy to misunderstand. When most of us hear that something has structure, we imagine a solid material. A planet has rock, a star has plasma, a loaf of bread has a crust, and, if things have gone well, a reasonably agreeable interior. A fuzzball is not simply a new material placed where the black hole used to be. Its proposed structure comes from the degrees of freedom available in string theory. Strings and brains can wrap, vibrate, carry charges, and form bound states in ways that do not have an ordinary everyday equivalent. The word surface can therefore be misleading too. It doesn't necessarily mean a hard shell like the surface of Earth. What matters is that the quantum state is not represented by the featureless interior of the simplest classical black hole solution. There is microstructure. And microstructure gives information somewhere to live. That's going to become one of our recurring questions. Where is the information? If a star collapses, where do all the quantum details describing that star go? If you throw something into the resulting object, where are the details describing that thing stored? If the object radiates, can those details return? And if they can return, why did Hawking's original calculation seem to say otherwise? Those questions sound philosophical, but they lead to very concrete mathematics. Black hole entropy has a precise formula. Hawking radiation has a calculable temperature. String theory has microscopic states that can be counted in particular cases. The mystery comes from trying to make all those pieces describe one consistent physical story. And that story begins long before anyone used the word fuzzball. It begins with the ordinary black hole, the clean one, the classical one. The black hole many of us first encounter in diagrams. A dark circle, perhaps surrounded by glowing material, with an event horizon marking the point of no return and a singularity concealed somewhere inside. That familiar image is useful, but it quietly combines several ideas that need to be separated. The dark region we draw on a page is not literally what an event horizon looks like. The singularity is not a tiny black marble sitting at the centre. The horizon is not a surface made of matter, and the interior is stranger than the common picture of a giant empty room with a dangerous point at the bottom. The strange thing about the fuzzball idea is that physicists first had to become very comfortable with an already strange picture. Long before anyone suggested replacing a black hole with strings and brains, general relativity had given us a remarkably clean description of what a black hole should be. From the outside, it could become almost absurdly simple. Matter could collapse in complicated ways, stars could spin, magnetic fields could twist around them, gas could crash together, and enormous amounts of radiation could escape during the process. But after the disturbance settled down, the black hole itself could be described using only a small number of properties. That simplicity is one of the reasons black holes became so useful to physicists. It is also one of the reasons they eventually became so suspicious. To understand the problem, imagine a large star nearing the end of its life. For most of the star's existence, two tendencies have been competing with each other. Gravity pulls the material inward. Pressure generated by the hot material and by nuclear reactions pushes outward. As long as those effects can balance each other, the star remains roughly stable. But stars do not have unlimited fuel. Eventually, the conditions inside some sufficiently massive stars can change so dramatically that the material can no longer support itself against gravity. The core collapses. Exactly what happens depends on the mass of the star and the details of the collapse. And not every dying star becomes a black hole. Some leave white dwarfs, some leave neutron stars. But if enough mass becomes concentrated into a sufficiently small region, general relativity allows the collapse to continue past a very important boundary. That boundary is the event horizon, and this is where the everyday picture can become misleading. People sometimes explain a black hole by saying that its gravity becomes so strong that the escape velocity exceeds the speed of light. That isn't a completely useless way to build intuition, but it isn't really how general relativity describes what is happening. A black hole is not simply an object with an unusually powerful gravitational pull, like a very heavy planet turned up to an unreasonable setting. The geometry of space-time itself has changed. Normally, if you are somewhere in space and want to leave, there are directions you can travel that take you farther away. You might need a powerful engine. You might need a great deal of fuel. You might need to reconsider why you went there in the first place, but outward paths exist. Inside an event horizon, the situation is different. All future-directed paths remain trapped. Even light directed outward cannot eventually reach the distant outside universe. That is why the event horizon is often called the point of no return. It's not because a physical wall prevents you from crossing back through it. There is no ordinary wall there at all. It is because once you are inside, the structure of space-time no longer provides a future route leading back outside. For a simple, non-rotating black hole, the size of this boundary is related to the black hole's mass. Increase the mass, and the horizon becomes larger. Decrease the mass, and it becomes smaller. A black hole with the mass of the Sun would have a horizon only a few kilometers across. The actual Sun, thankfully, has a radius of hundreds of thousands of kilometers, so it is nowhere close to being compressed enough to become one. And no, replacing Monday morning with a black hole would not solve the problem either. It would create several additional ones. One of the most important things to understand about an event horizon is that it is not made from material. If you approached a sufficiently large black hole in freefall, classical general relativity does not say that you would suddenly strike a shell at the horizon. There is no cosmic membrane waiting there like the surface of a planet. Locally, the crossing itself could be surprisingly uneventful. That statement often sounds impossible because diagrams usually draw the event horizon as a dramatic circle around a dark center. It looks like a boundary that ought to feel like something. But the horizon is a causal boundary. It tells us which events can communicate with the distant outside universe and which cannot. You would cross it at a definite point in your own experience. Your watch would keep ticking. Your thoughts would continue. Assuming the black hole was large enough that tidal forces at the horizon were not immediately destructive, you might not notice any sudden local change at the exact moment you crossed. Someone watching from very far away would describe your approach differently. Light signals you send outward would become increasingly redshifted and delayed. Each signal would lose energy as it climbed away from the black hole. To the distant observer, you would appear to slow down and fade near the horizon. This sometimes leads to the popular statement that an outside observer watches you freeze forever at the event horizon. That description needs care. The observer does not continue receiving a perfectly visible frozen image of you for eternity. Your signals become rapidly weaker, redder, and more difficult to detect. In practical terms, you disappear from view. From your own point of view, however, you cross the horizon after a finite amount of time. No contradiction is required. The two descriptions are using different ways of assigning time and distance in curved space-time. Once you cross, the situation becomes much less forgiving. In the simplest classical black hole, continuing toward the center is not merely one available option among several. It becomes part of your future. An analogy that is sometimes useful is to think about your relationship with tomorrow. You can walk north, south, east, or west, but you cannot choose to travel in a direction that prevents tomorrow from arriving. Inside the horizon of a simple black hole, moving towards smaller radial distance becomes somewhat like that. The geometry is arranged so that continuing toward the interior is unavoidable for any future directed path. Turning your rocket around does not provide an escape. Shining a flashlight outward does not provide an escape. Sending a strongly worded complaint to gravity does not provide an escape. The light itself is trapped, and according to the traditional classical description, deeper inside lies the singularity. This word has caused almost as much confusion as black hole. It is tempting to imagine the singularity as a tiny object sitting at the exact center. Perhaps an infinitely dense point. Perhaps a little bead containing everything that ever fell into the black hole. That picture is too literal. A singularity in general relativity is better understood as a sign that space-time, as described by the classical theory, cannot be continued normally. Certain paths through space-time come to an end after a finite amount of proper time. Curvature can become unbounded in familiar black hole solutions. The equations are telling us that the classical description has reached a limit. That distinction matters. Physicists do not usually look at an infinity appearing in a physical theory and celebrate because they have discovered a perfectly ordinary object whose density happens to be infinite. An infinity is often a warning. It may mean that the theory is being pushed beyond the conditions where it can give a complete description. General relativity does not include a quantum theory of gravity, so when it predicts extreme behavior deep inside a black hole, many physicists expect that quantum gravitational effects must eventually become important. The difficult question is where? The traditional expectation was that the dramatic quantum corrections would be confined to the deepest interior, close to the singular region where curvature becomes enormous. Everywhere else, especially around the horizon of a large black hole, ordinary semi-classical space-time seemed perfectly reasonable. That assumption will become extremely important when we return to fuzzballs. For now, imagine the classical black hole as having two very different regions. Outside the horizon, space-time can be calm. You can orbit the black hole. You can observe matter around it. You can send signals away. If the black hole is isolated and sufficiently massive, you could remain at a safe distance for as long as your food supply and tolerance for terrible holiday destinations allowed. Inside the horizon, escape is impossible. Farther inward, the classical description ends at a singularity. Simple enough, or at least simple by black hole standards. The first exact black hole-like solution of Einstein's equations came from Carl Schwarzschild in 1916, only shortly after Einstein completed general relativity. Schwarzschild studied the gravitational field outside a spherical non-rotating mass. The solution contained a particular radius that initially looked mathematically troublesome. In the coordinates being used, expressions behaved strangely there. For years there was confusion about what that surface actually represented. Was it a physical singularity? Was something pathological happening there? Better coordinate systems eventually made the distinction clearer. The apparent problem at what we now call the horizon could be removed by changing coordinates. The deeper singularity could not be removed in the same simple way. That was an important clue. The horizon was not necessarily a place where physics itself broke. The central singular behavior was another matter. Then black holes became more realistic. Real astronomical objects rotate. Stars rotate. Gas clouds rotate. Planets rotate. Almost everything in astronomy seems to acquire angular momentum and then stubbornly refuse to give it back, so a realistic black hole should usually rotate as well. In 1963, Roy Kerr found the solution describing a rotating black hole. A Kerr black hole is considerably more complicated than the simple non-rotating Schwarzschild case. Rotation changes the geometry. Outside the event horizon is a region called the ergosphere, where space-time is dragged around by the rotating black hole so strongly that an observer cannot remain stationary relative to distant stars. This effect is related to frame dragging. The black hole's rotation is, in a very real sense, affecting how space-time behaves around it. The mathematical interior also becomes more complicated. The ideal Kerr solution contains an inner horizon and a ring-shaped singular structure rather than the simple central singularity of a non-rotating solution. But there are serious questions about the stability of parts of that idealized interior. Small disturbances can become enormously amplified near the inner horizon, so when people casually draw a rotating black hole and then begin discussing passages through other universes, wormholes, or convenient shortcuts to somewhere interesting, they have usually moved several steps beyond what we can confidently expect from a black hole formed in the real universe. General relativity is generous with mathematically interesting possibilities. Nature is under no obligation to keep all of them open for visitors. Still, one feature of the traditional exterior picture remains strikingly simple. Once a stationary black hole settled down, much of the detailed information about the matter that formed it seemed inaccessible from outside. A star might have been made from an enormous number of particles arranged in a fantastically complicated state. Every atom had a history, every particle had quantum properties. The collapsing material had temperature, composition, density variations, magnetic fields, and countless microscopic details. Yet the resulting stationary black hole could look almost featureless. In the familiar classical description, the important externally measurable parameters were essentially its mass, angular momentum, and electric charge. This idea became associated with the phrase, "black holes have no hair." The hair is a metaphor for distinguishing features. A person can be identified by hairstyle, colour, length, curls, or the fact that the morning has clearly gone badly. A classical black hole seemed to lose most of those distinguishing details. Two black holes with the same mass, charge, and spin could look identical from outside even if they had formed from very different collections of matter. The phrase is useful, but it shouldn't be treated as an unrestricted law applying to every gravitational theory and every possible field. The precise mathematical uniqueness results depend on assumptions. For the standard black holes of general relativity under the usual conditions, however, the message was powerful. Black holes seemed extraordinarily simple on the outside. That simplicity created an odd contrast. A black hole could be formed from something complicated, yet the final object seemed to remember very little that an outside observer could measure. Imagine taking an entire library and compressing it into a device with only 3 numbers displayed on the front. Mass, charge, spin. You could throw in Shakespeare, you could throw in tax records, you could throw in the instruction manual you needed yesterday, but have now finally found. After the black hole settled down, the external gravitational description would not provide a convenient catalogue of what went in. Classically, this did not immediately create a disaster. The information could simply be regarded as hidden inside. You could say that the details crossed the event horizon and became inaccessible to outside observers. That is inconvenient, certainly, but inaccessible is not the same as destroyed. If you lock a notebook in a safe and throw away the key, you may never read the notebook again. But the words have not ceased to exist simply because you cannot retrieve them. The event horizon seemed capable of playing a similar role. Information could go in. It could remain inside. The outside universe simply could not get it back. If black holes lasted forever, that story might have remained uncomfortable but manageable. Then another clue appeared. Black holes behaved suspiciously like thermodynamic objects. This was surprising because classical black holes had originally seemed almost perfectly cold and featureless. But researchers noticed a remarkable connection between the area of a black hole's event horizon and the laws of thermodynamics. Under suitable classical conditions, the total area of black hole horizons does not decrease. Entropy in thermodynamics also has a tendency not to decrease in an isolated system. The similarity was difficult to ignore. Jacob Bekenstein took it seriously. He proposed that a black hole should have entropy proportional to the area of its event horizon. That idea immediately raises a question that turns out to be central to everything we're discussing. What does black hole entropy count? In ordinary statistical mechanics, entropy is connected with microscopic possibilities. A gas in a box can look the same macroscopically, while its molecules occupy an enormous number of different microscopic arrangements. Temperature, pressure, and volume give you a useful large-scale description, but underneath that description are countless possible configurations. Entropy tells you something about how many microscopic states are compatible with the macroscopic state. If a black hole has entropy, perhaps it also has microscopic states, but where are they? The classical black hole did not appear to contain visible surface molecules. The horizon was not supposed to be a material shell. The exterior geometry was almost completely characterized by a few parameters. The deep interior ended in a region where the classical equations failed. So what microscopic configurations were responsible for the entropy? At first, that question could be left somewhat open. Perhaps whatever the complete quantum theory of gravity turned out to be would provide the answer. General relativity was not expected to explain microscopic quantum states by itself. Then Stephen Hawking performed a calculation that changed the status of the problem. He considered quantum fields in the space-time around a black hole. The result was extraordinary. Black holes should radiate, not because ordinary material is escaping from inside the horizon, not because the singularity is firing particles outward, and not, in the more careful description, because one particle of a simple particle-antiparticle pair casually tumbles into the horizon while its partner flies away, although that popular picture is sometimes used as a rough visual aid. Hawking's calculation showed that quantum fields in the black hole spacetime lead a distant observer to detect thermal radiation. A black hole has a temperature. For a simple black hole, larger mass means lower temperature. Astrophysical black holes are therefore extremely cold. A stellar mass black hole has a Hawking temperature far below the temperature of the cosmic microwave background around us today, so ordinary astrophysical black holes are not currently sitting in empty space rapidly steaming themselves away. The effect matters enormously in principle, though. A black hole can lose energy. If conditions eventually allow Hawking emission to dominate over energy entering the hole, it can shrink. Given enough time, the standard semi-classical calculation suggests that it can evaporate. Now our comfortable old explanation has a serious problem. Before Hawking radiation, we could imagine information falling through the horizon and remaining inside forever. After Hawking radiation, the black hole itself no longer necessarily remains forever. Suppose we create a black hole from matter in some definite quantum state. More matter falls in. The black hole radiates. It becomes smaller. Eventually, if evaporation goes all the way to completion, the black hole disappears. What remains? Radiation. So the obvious hope would be that the radiation carries the information back out. That is what quantum mechanics seems to require. If the full evolution begins from a particular quantum state, the final state should retain the information necessary, at least in principle, to distinguish it from other possible initial states. The information may become fantastically scrambled. Recovering it might be so impractical that no civilization could ever accomplish the task. That is fine. Quantum mechanics does not promise convenient filing systems. It does require a certain kind of consistency. Hawking's original result seemed to create something else. The radiation appeared thermal. Its detailed form seemed determined by simple properties of the black hole, rather than by all the microscopic details of what had fallen inside. Imagine two black holes with the same macroscopic properties. Into one, you throw a carefully arranged collection of matter representing one quantum state. Into the other, you throw something arranged differently. If both evaporate into radiation that carries no corresponding distinction, then different initial states can lead to the same final thermal state. The detailed quantum information has vanished from the description. We can no longer simply say that it is safely sitting behind the horizon. There may eventually be no horizon. There may eventually be no black hole. There is nowhere obvious left to hide the notebook. And this is where the old picture becomes more than merely strange. The assumptions that looked harmless when considered separately begin to pull against one another. General relativity gives us a smooth horizon for a sufficiently large black hole. Quantum field theory in that space-time gives us Hawking radiation. The ordinary interior allows infalling information to continue away from the outside universe. The black hole can then evaporate. Quantum mechanics says information should be preserved. Those statements do not fit together easily. Something has to change, or at least something in our understanding has to be incomplete. For a long time, many possible escape routes were considered. Perhaps information really is destroyed. Perhaps evaporation stops and leaves behind a tiny remnant containing everything. Perhaps information somehow escapes through the Hawking radiation, despite the original semi-classical calculation. Perhaps the interior connects to something else. Perhaps the concept of the horizon needs modification. Each possibility comes with consequences, and the closer physicists examined the problem, the harder it became to make a small adjustment, while leaving every other part of the familiar black hole untouched. This is precisely the pressure that eventually makes ideas like fuzzballs less ridiculous than the name initially suggests. Because if the horizon is completely smooth and empty in the traditional way, and if information can cross it without leaving accessible structure behind, then Hawking's calculation becomes extremely difficult to evade. The problem is not confined to the singularity. Waiting until the infalling matter reaches the centre may already be too late. The information has become causally separated from the outgoing radiation, so the question begins moving outward. That question sounds simple enough. A black hole forms from ordinary matter, it eventually radiates away, and we ask what happened to the information describing everything that went into it. But before we can answer that, we need to be careful about what physicists mean by information, because they don't mean a list of interesting facts about the objects that disappeared. If you throw an encyclopedia into a black hole, the information paradox is not mainly concerned with whether the universe can still remember the population of Belgium. If you throw in a photograph, it is not asking whether the picture can somehow be printed back out of the Hawking radiation. And if you throw in your phone, the universe is under no obligation to recover your password, although it would be a very impressive customer service feature. The information in question is quantum information. A physical system is described by a quantum state. That state contains the information needed in principle to determine the probabilities of possible measurement outcomes and to distinguish that state from other possible states. Quantum mechanics allows the state to evolve in complicated ways. It can spread out. Different parts can become entangled. Information can become hidden in correlations between many particles. Something that started in a simple state can become so thoroughly scrambled that recovering the original details would be fantastically difficult. But difficulty is not the problem. Quantum mechanics is perfectly comfortable with scrambled information. What it does not ordinarily allow is information simply being erased by the fundamental evolution of an isolated system. This property is often described using the word unitarity. We don't need the mathematical machinery behind that word tonight. The important idea is that quantum evolution preserves enough information about the initial state that the evolution can, in principle, be reversed. Not easily reversed, not practically reversed. You do not need to be able to collect every atom of smoke from a burned book and rebuild the pages. The claim is more basic. At the fundamental quantum level, the final state should still contain correlations that depend on the initial state. Burning a book does not destroy its quantum information in the way a paper shredder destroys your ability to read the sentences. The information spreads into the ash, the smoke, the thermal radiation, the surrounding air, and countless microscopic correlations. Good luck recovering it. But quantum mechanics says it has not simply been deleted. A black hole appears to offer deletion. Suppose we begin with some matter in a pure quantum state. A pure state means, roughly speaking, that we have the most complete quantum description available for the system. There may still be uncertainty in individual measurements, because quantum mechanics includes probabilities, but we are not merely ignorant of which state the system is in. Now allow that matter to collapse into a black hole. The black hole sits there for a very long time, then it emits Hawking radiation. Eventually, if we follow the semi-classical calculation all the way through, the black hole evaporates. The final state appears thermal. A thermal state is characterized by things such as temperature. It does not obviously preserve the detailed distinctions between all the different pure states that could have formed the black hole. That gives us a process that seems to take many different possible beginnings and produce the same kind of final result. Pure state in, thermal mixed state out. And that is the problem Hawking emphasized. A mixed state is not merely a complicated pure state. The distinction matters. Imagine I place a coin in a box. If I know the coin is definitely heads up but simply refuse to tell you, then from your perspective there is uncertainty. But the coin still has a definite arrangement. Quantum mixed states are described more carefully than ordinary hidden ignorance, but the comparison gives us a hint. In the black hole problem, the concern is that after evaporation, the outside universe may be left with a state that genuinely lacks access to information that belonged to the complete initial quantum state. The evolution would no longer be unitary. Something about the usual rules of quantum mechanics would have to change. Hawking initially argued that this was exactly what black holes did. Black holes, in that view, did not merely hide information, they destroyed it. That is a remarkably serious claim. Quantum mechanics is not a small theory used for one narrow corner of physics. It underlies our description of atoms, particles, chemistry, materials, lasers, electronics, and much of modern physics. Allowing information to disappear fundamentally is not like discovering that one particular equation needs a slight correction. It changes the structure of the theory. So physicists naturally asked whether the information might be escaping in some subtle way that Hawking's first calculation had missed. To understand why that is difficult, we need to look a little more closely at the radiation itself. Hawking radiation comes from quantum fields in curved space-time near a black hole. You may have seen a popular explanation involving pairs of particles appearing near the event horizon. One particle falls inward, the other escapes. The escaping particle becomes Hawking radiation. That picture can be useful for intuition, but it should not be taken too literally. Hawking's actual calculation involves quantum fields and the way different observers define particles in the curved space-time around a black hole. Still, the pair picture helps us understand one crucial feature. The outgoing radiation is entangled with degrees of freedom associated with the black hole interior. Entanglement is one of those quantum words that has escaped physics departments and now appears almost everywhere, usually just before someone says something that makes a physicist stare quietly at the floor. In quantum mechanics, two systems can share a joint state in such a way that neither system has a complete independent description of its own. Their properties are correlated at the level of the quantum state. Suppose an outgoing Hawking quantum escapes toward distant space while its partner is associated with the interior. Taken together, the pair can be in a pure state. But if you only look at the outgoing particle and ignore the interior partner, the outgoing part appears mixed. Then another Hawking quantum escapes. It too is entangled with something left behind. Then another, and another. The radiation outside the black hole becomes increasingly entangled with the degrees of freedom that remain inside. This does not immediately seem disastrous. The information could still exist in the combined system. Outside radiation plus black hole interior. Together, everything might remain perfectly quantum mechanical. If the black hole stayed around forever, we might once again say that the missing information was simply inaccessible. But evaporation prevents us from stopping there. As the radiation continues, the black hole loses mass. Its horizon shrinks. The remaining object gets smaller. At some point, we have an uncomfortable accounting problem. More and more radiation is outside, less and less black hole remains inside. Yet if each new piece of radiation continues to become entangled mainly with partners behind the horizon, the amount of entanglement between the radiation and the remaining black hole keeps increasing. Eventually the black hole is supposed to disappear. What is the outside radiation entangled with then? There is no interior left in the ordinary evaporation picture. No large black hole remains. No familiar location exists where all the partner degrees of freedom can continue hiding. We have collected a great deal of radiation, but according to the simplest Hawking calculation, that radiation still looks thermal. The problem has not been solved. We have merely waited until the cupboard containing the missing information has vanished. Don Page sharpened this issue by asking what the radiation should look like if black hole evaporation really is unitary. Instead of accepting that the final state loses information, suppose quantum mechanics remains valid. Then the information must somehow emerge in the radiation. But it does not necessarily need to emerge immediately. A newly formed black hole could radiate in a way that looks almost thermal for a very long time. The information could be hidden in incredibly subtle correlations among the radiation particles. At first, the entanglement entropy of the radiation could rise. That makes sense. The radiation is becoming entangled with the black hole, but if the entire process is unitary and the black hole eventually disappears, that entropy cannot simply keep rising until the end. At some stage, it has to turn around. As more radiation comes out, the radiation must begin carrying correlations that purify the earlier radiation. The entropy should eventually decrease back towards zero when the evaporation is complete. If you draw that behavior on a graph, you get what is now called the Page curve. At the beginning, the curve rises. Later, it reaches a maximum, then it falls. The rough point where the behavior changes is known as the Page time. For a black hole evaporating unitarily, This is around the stage when a substantial fraction of the original black hole entropy has effectively been transferred into the radiation. Before that point, the outgoing radiation can look nearly thermal without immediately causing trouble. After that point, things become much more demanding. New radiation has to contain information about the black hole. It must be correlated with radiation that escaped earlier, and now we run into an argument that sounds innocent until you try to make all the pieces fit. According to the smooth horizon picture used in Hawking's calculation, a newly emitted Hawking quantum should be strongly entangled with a partner mode across the horizon. That relationship is part of what makes the region near the horizon look like ordinary vacuum to an infalling observer. But if the black hole is old enough, quantum unitarity says the new outgoing quantum also needs the right correlations with the earlier Hawking radiation, so that the total radiation begins becoming less mixed. One quantum system cannot be maximally entangled in both ways at once. Quantum entanglement has rules. It cannot be freely copied and distributed wherever the argument needs it. This tension later became central to the firewall debate, which we'll return to when we discuss what an observer might encounter near a black hole. For the moment, the important point is simpler. Keeping a completely ordinary horizon while also requiring information to emerge in the radiation becomes extremely difficult. Perhaps you might think Hawking's calculation is only approximate. And that is true. Maybe the radiation is not exactly thermal. Perhaps each outgoing particle carries an extremely tiny correction. One particle differs very slightly depending on what entered the black hole. The next particle differs a little too. Over an enormous number of emissions, maybe all those tiny corrections add up. By the end, perhaps they encode the complete initial state. That sounds reasonable. It also turns out not to be enough under the usual assumptions. Samir Mathur formulated the issue in terms of entanglement, and showed that small corrections to the ordinary Hawking pair state cannot remove the growing entanglement required by the leading calculation. If the near-horizon physics remains almost exactly the traditional smooth vacuum picture, tiny corrections do not rescue the information. The necessary change has to be substantial. This is one of the steps that leads directly toward fuzzballs. The paradox is sometimes described casually as if physicists simply forgot that quantum gravity exists. Of course, the calculation will receive quantum corrections, the argument goes. General relativity is classical. Near a black hole, quantum gravity should fix everything. Problem solved. Unfortunately, saying quantum gravity is not the same as demonstrating a mechanism. If the quantum gravity effects only become important in a tiny region deep near the classical singularity, then they may not be able to change the entanglement being created much farther out near the horizon. By the time the information reaches the deep interior, the outgoing radiation has already escaped. To restore unitarity, something has to alter the process that creates that radiation, or alter our understanding of what counts as inside and outside. The required effect cannot simply sit quietly at the centre and hope the bookkeeping improves. This is why the location of quantum gravity becomes as important as its strength. In the traditional picture, a large black hole has weak curvature at its horizon. If the black hole is enormous, crossing that horizon should not expose you to Planck-scale conditions. There is nothing obviously violent there, so ordinary intuition says quantum gravity effects should be tiny at the horizon. But the information paradox says that if those effects are always tiny there, the entanglement problem persists. One line of reasoning seems to say, nothing unusual should happen here. Another says, something important has to happen here. Black hole physics has a habit of arranging disagreements in exactly the least convenient places. There have been many proposed responses. One possibility is that information really is destroyed. That would accept Hawking's original conclusion and modify quantum mechanics. Most modern approaches to quantum gravity do not favour that solution, particularly because theories such as string theory and the gauge/gravity duality strongly suggest unitary evolution in settings where black holes can be described. Another possibility is that evaporation never fully finishes. Perhaps a tiny remnant remains behind, storing all the information. At first, that sounds wonderfully economical. Make the final black hole very small, put everything inside it. Leave it there. Unfortunately, an object with a tiny mass would need to encode an enormous number of possible states if it can store the information from arbitrarily large black holes. That creates its own theoretical difficulties. It is a very small box being asked to run the universe's least practical archive. Another proposal says the information escapes at the very end of evaporation. Again, the storage problem becomes severe. A nearly evaporated black hole would somehow have to retain an immense amount of information and then release it during the final stage. There have also been ideas involving black hole complementarity. From the viewpoint of a distant observer, information might be absorbed and processed by degrees of freedom associated with a stretched horizon and later returned in radiation. From the viewpoint of an infalling observer, the same information might appear to pass smoothly through the horizon. Perhaps no single observer could compare both descriptions and discover a contradiction. That idea was enormously influential, but entanglement arguments made the situation increasingly uncomfortable, especially for old black holes. Eventually, the firewall argument sharpened the conflict. Unitarity, ordinary low-energy physics outside the horizon, and a completely uneventful horizon for an infalling observer cannot all be maintained in the simplest way. We will save the unfortunate possibility of arriving at a horizon and being immediately cooked for later. It is not ideal material for the beginning of a restful evening. The broader lesson is enough for now. The information paradox does not arise because black holes are mysterious places and physicists dislike mysteries. It arises from a very specific conflict among theories that work extremely well. Quantum mechanics says information is preserved. General relativity gives us black holes with horizons. Quantum field theory on that curved space-time gives us Hawking radiation. The traditional horizon allows one member of the entangled pair to disappear inward while the other escapes. Evaporation eventually removes the black hole. Put those ingredients together and the final state does not behave the way unitary quantum mechanics says it should. Remove one ingredient and you risk damaging a theory supported by an enormous amount of successful physics. Keep all of them exactly as they are, and the paradox remains. That is why the problem has survived for so long. It is not difficult because no one has thought of an explanation. There have been many explanations. It is difficult because every solution has to preserve several pieces of physics at once. And there is another clue hiding in the black hole's entropy. Remember that the entropy is proportional to the area of the horizon. Entropy ordinarily counts microscopic states. If a black hole has a huge entropy, it should have a huge number of microscopic configurations. From far away, those configurations somehow look almost identical. Same mass, same charge, same angular momentum, but microscopically, there must be an extraordinary variety of ways to build what the classical theory calls one black hole. That changes the question. Instead of asking only, how does information escape from a black hole? We can ask something more basic. What is a black hole made of at the quantum level? If the answer is that it really does have microscopic degrees of freedom, perhaps those degrees of freedom can store and release information. Perhaps Hawking radiation is only perfectly thermal when we ignore the details of the underlying state. Perhaps the smooth, empty-looking horizon is an approximation that emerges after we average over many different microstates. Or perhaps the classical geometry is missing structure much larger than anyone originally expected. These possibilities are not automatic solutions. They have to come from an actual quantum theory of gravity. They need microscopic states that can be counted. They need enough states to reproduce black hole entropy. They need a mechanism for radiation that can depend on the state. And ideally, they should explain why ordinary general relativity works so well outside the black hole, even if the microscopic picture underneath is radically different. This is where string theory becomes useful. Not because the words tiny vibrating strings magically remove the paradox. They do not. The important breakthrough came when string theory provided a setting in which physicists could actually identify and count microscopic configurations corresponding to certain black holes. For the first time, the enormous entropy written on the black hole's horizon could be matched by an enormous number of specific quantum states. And when researchers began asking what those states looked like in space-time, some of them did not resemble the old picture of an empty horizon surrounding a conventional interior. When physicists say that a particle might actually be a tiny string, they are not suggesting that an electron contains a miniature piece of thread that could somehow become tangled around a proton. String theory uses the word string in a very specific mathematical sense. The basic object is one-dimensional. A point has no length. A string has length, although the characteristic length involved in fundamental string theory would be extraordinarily small, and that small change, replacing a zero-dimensional point with a one-dimensional object, turns out to have enormous consequences. To see why anyone would consider doing this, it helps to begin with the picture used in ordinary particle physics. The standard model describes elementary particles such as electrons and quarks as point-like objects. As far as experiments have been able to determine, an electron does not have a little solid surface. It does not appear to be a microscopic marble. We treat it as having no measurable internal size. The same basic approach works extremely well for the other elementary particles. Quantum field theory then describes these particles as excitations of underlying fields. An electron is associated with the electron field. A photon is an excitation of the electromagnetic field. Quarks belong to their own fields. This framework is extraordinarily successful. It has survived precise experimental tests and explains a remarkable amount of the physics we observe. String theory did not arrive because physicists suddenly discovered that electrons were definitely little loops. There is no experimental evidence showing that elementary particles are strings. Historically, the idea developed through attempts to understand patterns in the strong nuclear interactions, before quantum chromodynamics became established as the correct theory of those interactions. Researchers studying certain mathematical models of particle scattering noticed that the equations behaved as though the underlying objects were not points, but tiny vibrating strings. At first, the strings were being considered in connection with hadrons, particles such as protons and neutrons and their relatives. Then physicists discovered something in the mathematical spectrum that changed the direction of the entire subject. The theory contained a massless particle with spin 2. That might sound like a rather unremarkable technical detail. It wasn't. A consistent massless spin 2 particle has exactly the kind of properties expected of the hypothetical quantum particle associated with gravity, the graviton. Suddenly, a framework that had been developed for one problem appeared to contain gravity, whether anyone had asked for it or not. It was a little like building a calculator and discovering that one of the buttons operates a small but perfectly functional submarine. At that point, researchers began taking seriously a much more ambitious interpretation. Perhaps the strings were not models of particular composite particles. Perhaps strings were fundamental. In that picture, the different elementary particles we observe could correspond to different quantum states of the same basic kind of object. This is where the phrase vibrating strings usually appears. It is useful, provided we don't take it too literally. Imagine an ordinary guitar string. It can vibrate in different patterns. There is a fundamental mode, and there are higher harmonics. Different patterns produce different sounds. The string itself remains the same string, but its state of vibration changes what you hear. A fundamental string in string theory also has different possible excitation modes. When the string is quantized, those different modes correspond to different particle states with different masses, spins, charges, and other properties. One excitation can behave like one kind of particle. Another excitation behaves like another. In that sense, what we normally call different particles can be understood as different ways the underlying string exists quantum mechanically. The guitar analogy should be retired before it becomes too enthusiastic, though. A fundamental string is not vibrating through ordinary air. It does not make sound. It is not made from smaller pieces of material, and the vibration is described by quantum mechanics rather than by the sort of visible wobbling you might see when someone plucks a string. Still, the central idea is useful. Instead of nature requiring a completely separate fundamental object for every particle, a single type of extended object can possess many possible quantum states. There are two especially important basic forms. A string can be open, meaning it has two endpoints, or it can be closed, meaning it forms a loop. A closed string has no endpoints at all. Imagine taking a tiny piece of thread and joining the ends together, except that this thread is not really thread, may exist at a scale vastly beyond anything we can directly inspect, and requires a substantial amount of mathematics before breakfast. Open and closed strings have different spectra of quantum states. One of the most important states of a closed string is the massless spin 2 state associated with the graviton. That is a major reason gravity is built so naturally into string theory. If you quantize a suitable closed string, you don't have to bolt gravity onto the theory afterward as an optional accessory. A gravitational state is already there. This matters because gravity has always been difficult to reconcile with quantum mechanics, using the same methods that work for the other fundamental forces. The electromagnetic, weak, and strong interactions are successfully described using quantum field theories. Gravity is described extremely well at large scales by Einstein's general relativity, but if we simply try to quantize gravity in the most straightforward point-particle way and then push calculations to arbitrarily high energies, troublesome infinities appear that cannot be handled using the ordinary renormalization methods in the same way as they can in familiar renormalizable quantum field theories. String theory changes the short-distance description, because interactions are no longer confined to perfectly sharp points. Consider two ordinary point particles interacting. In a simple diagram used in quantum field theory, interaction events occur at definite spacetime points. Lines meet at vertices. The mathematics has to account for physics at arbitrarily tiny distances around those interaction points. A string behaves differently because it is extended. As it moves through time, a point particle traces out a line called a world line. A string traces out a two-dimensional surface called a world sheet. An interaction can occur when strings split or join. One closed string can divide into two can join into one. Open strings can join at their endpoints or rearrange in other allowed ways. The resulting history looks smoother than a collection of point-like lines, meeting at a single infinitely sharp vertex. This extended structure changes the high-energy behavior of the theory. It is one of the reasons string theory became such an important candidate for a quantum theory that includes gravity. But there is a price. There is almost always a price. The mathematics only remains consistent under special conditions. One of the first surprises is dimensionality. We experience three large spatial dimensions: left and right, forward and backward, up and down. Add time, and everyday relativity describes a four-dimensional space-time. Superstring theories, however, are naturally formulated in 10 space-time dimensions. That gives us 9 spatial dimensions and 1 time dimension. At this point, it is reasonable to look around the room and check whether 6 additional directions have appeared while you weren't paying attention. They probably haven't. String theory deals with this using compactification. The idea that additional spatial dimensions might be compact is older than string theory itself. A dimension can exist but be curled up so tightly that it is difficult to notice at ordinary scales. A common analogy uses a garden hose viewed from far away. From across a field, the hose looks like a one-dimensional line. An ant standing on the hose would disagree. The ant can travel along the hose, but it can also move around its circular surface. That second direction was always there. You simply couldn't see it from far away. Extra dimensions in string theory would be far more complicated and far smaller than the circular direction around a hose, but the general idea is similar. Some dimensions could be extended and easily visible. Others could be compactified into tiny geometries. Strings can interact with those compact dimensions in ways that point particles cannot. For example, a closed string can wrap around a compact dimension. It can also carry quantized momentum associated with motion through that dimension. These possibilities will become extremely important for black holes, not immediately. For the moment, it is enough to notice that extra dimensions are not merely decorative additions to string theory. The way they are shaped can influence the physical properties seen in the lower dimensional world. Different compactification geometries can produce different particle spectra and interactions. This is one reason deriving the exact physics of our universe from string theory is difficult. There are many possible configurations. String theory gives you a very large menu. Nature has so far neglected to leave the order receipt on the table. Another ingredient enters when we try to construct theories containing both bosons and fermions in a consistent way. Particles are broadly divided into these two categories. Bosons include particles such as photons. Fermions include particles such as electrons and quarks. A realistic theory of nature obviously needs fermions, since a universe containing no electrons or quarks would make tonight's listening arrangements rather difficult. Superstring theory incorporates a symmetry called supersymmetry. Supersymmetry relates bosonic and fermionic degrees of freedom. In the simplest description, each type of bosonic state is connected by the symmetry to a fermionic partner, and vice versa. We have not observed the straightforward supersymmetric partner particles that many simple models would lead us to expect at accessible energies. That means supersymmetry, if it is relevant to nature, cannot appear in the most obvious unbroken form at the energies we have explored. This remains one of the unresolved issues when connecting string theory to observed particle physics. For the Fuzzball story, however, supersymmetry becomes useful for a different reason. Certain highly supersymmetric states can be mathematically controlled, even when interactions become strong. Some quantities associated with these states remain protected as the strength of the interaction changes. That gives physicists a remarkable tool. They can sometimes count microscopic states in a regime where the calculation is manageable, and then relate that count to a gravitational description in another regime. That sentence may not sound especially dramatic. A few decades ago, it helped produce one of the most important successes in string theory black hole physics. We'll get there shortly. First, there is another feature of strings that matters for understanding how complicated states can form. Strings have tension. An ordinary stretched string wants to contract because of its tension. A fundamental string also has a characteristic tension, although again this is a quantum object, not a microscopic elastic band. The tension is related to the fundamental string scale. Exciting a string generally costs energy. Higher excitation modes can therefore correspond to more massive particle states. At energies available in ordinary experiments, if the fundamental string scale is extremely high, these massive string excitations would be far beyond our ability to produce. The low-energy world could then look as though it were made from point particles. This gives a useful explanation for why we do not see tiny strings waving around in particle detectors. If strings exist at a scale far smaller than anything we can currently resolve, then an experiment performed at much larger distances would see only their low-energy particle-like states. There is a simple everyday comparison. Look at a piece of string from across a large room. You might see a thin line. Move far enough away and even that disappears into something that looks effectively like a point. The detailed structure is still there. Your resolution is simply insufficient to detect it. With fundamental strings, the gap between the proposed microscopic scale and our direct experimental reach may be enormous. This also means we should be careful when someone asks how big a string is. The theory contains a characteristic string length, related to the parameter usually written as the square root of alpha prime. But quantum strings do not behave like rigid little rods of one fixed length sitting on a ruler. Their states can have different spatial profiles, and highly excited strings can become complicated extended objects. That flexibility becomes particularly interesting when enormous numbers of stringy degrees of freedom are combined. A black hole is exactly the sort of situation where enormous amounts of energy and entropy are packed into a relatively compact region. At first glance, you might expect string theory to reproduce the familiar black hole and merely make a small correction near its singularity. That was a natural assumption. Far outside the black hole, the low-energy limit of string theory includes gravity, described by equations closely related to general relativity. If the black hole is large, the curvature at its horizon can be gentle compared with the fundamental quantum gravity scale. It would therefore seem reasonable to use the ordinary classical geometry almost everywhere and reserve the genuinely stringy behaviour for the deepest interior. But string theory contains more than the simple fundamental strings we've been discussing. That became increasingly clear as physicists discovered relationships among apparently different versions of the theory. By the 1980s, researchers had identified several consistent superstring theories. There was Type 1, there were Type 2a and Type 2b. There were two heterotic theories. For a theory hoping to provide a fundamental description of nature, having 5 candidates was slightly awkward. Imagine announcing that you've discovered the final menu and then handing everyone 5 different menus. During the 1990s, however, physicists discovered increasingly powerful dualities connecting these theories. A duality says that 2 apparently different descriptions can actually represent the same underlying physics. One theory may be useful when interactions are weak. Another description of the same system may become useful when interactions are strong. Objects that look elementary in one description may appear as complicated composite objects in another. Large distances can sometimes be related to small ones. Momentum in a compact direction can be related to strings wrapping around that direction. The different string theories stopped looking like 5 completely separate candidates and began looking like different limits of a deeper connected framework. That broader framework is often associated with M theory, although a complete formulation of M theory in every setting remains a difficult subject of its own. For our purposes, the important lesson is that strings were no longer the only fundamental-looking objects in the game. The theory also contained extended objects with more spatial dimensions. A string extends in one spatial direction. Another object could extend in 2, another in 3, or more. Physicists use the general word brane, derived from membrane, for these higher dimensional objects. A 0-dimensional brane is point-like, a 1-dimensional brane is string-like, a 2-dimensional brane resembles a membrane. Higher dimensional versions continue the pattern, although visualizing a 6-dimensional brane is an excellent way to discover that the human imagination has office hours. Among the most important are D-branes. They emerged as essential physical objects in string theory rather than optional mathematical conveniences. Open strings can end on them, and D-branes can carry particular conserved charges. This discovery completely changed the kinds of systems string theorists could construct and analyze. D-branes could form bound states. Strings could stretch between them. Momentum could move along compact directions. Branes could wrap around extra dimensions. Different charges could be combined. A complicated object could be built from many interacting components while still being controlled mathematically in special circumstances. And black holes began to reappear in a new form. Suppose you arrange certain strings and branes with particular charges. When the gravitational coupling is weak, you may be able to describe the system as a collection of stringy objects and count its possible quantum states. Increase the effective gravitational interaction, and the same collection can acquire a description that looks, from far away, like a black hole. That connection is precisely what makes string theory relevant to our information problem. Remember what black hole entropy had been asking us. What are the microscopic states? General relativity gave us the large-scale geometry. It gave us the horizon. It gave us the mass, charge, and rotation. Thermodynamics told us that the black hole had entropy proportional to its horizon area. But ordinary classical geometry did not tell us what microscopic configurations the entropy was counting. String theory could ask the question differently. Instead of beginning with a smooth black hole and wondering what invisible states might somehow live inside it, start with objects whose quantum states we know how to count: strings, branes, momentum, charges, bound states. Then ask whether a large collection of those ingredients produces the same entropy as the corresponding black hole. In 1996, Andrew Strominger and Kumran Varfa did exactly this for a particular class of supersymmetric 5-dimensional black holes. They counted the degeneracy of the relevant string theory bound states. The resulting microscopic entropy matched the Bekenstein-Hawking entropy of the black hole. That result did not prove that every black hole in the universe is a fuzzball. It did something more basic and extremely important. It showed, in a controlled string theory example, that black hole entropy really could arise from identifiable microscopic quantum states. The enormous number in the entropy formula was not necessarily an abstract thermodynamic label attached to a featureless geometry. There were actual states to count, and there were enough of them. This takes us back to the question that has been following us since Hawking radiation entered the discussion. If all those microstates exist, what do they look like? From very far away, they must resemble the same black hole closely enough that the familiar gravitational description works. Otherwise, the entropy calculation would not be describing the object we wanted. But when you move closer, do all the microstates still contain exactly the same smooth event horizon and exactly the same empty-looking interior? Or does the microscopic structure become visible? If every distinct state looks identical everywhere outside an ordinary horizon, then the differences among the states are somehow hidden behind that horizon, and we're back near the information problem we started with. But if the states have physical structure that reaches outward, then the exterior may contain more information than the classical black hole geometry suggests. That possibility did not come from replacing the word particle with the word string and declaring victory. It came from learning that string theory possesses a much richer collection of extended objects than anyone initially expected. Fundamental strings were only the beginning. A fundamental string gives us a one-dimensional object with different quantum states. Branes expand that idea by allowing string theory to contain objects extended across more spatial dimensions. Physicists usually label them according to the number of spatial dimensions they occupy. A D0 brane is point-like. A D1 brane extends along one spatial direction. A D2 brane extends along 2. A D3 brane extends along 3. And the pattern continues. The letter D comes from Dirichlet, referring to a particular type of boundary condition in the mathematics of string theory. Unless you've been hoping to relax tonight with a detailed discussion of differential equations and boundary conditions, we can leave most of that machinery comfortably on the shelf. The physical idea is more useful for us. Open strings have endpoints. Those endpoints can be attached to D-branes. So rather than imagining a brane as a solid sheet made from ordinary material, think of it as an extended object on which certain strings are allowed to end. This immediately makes the system much richer. A string can begin and end on the same brane. It can stretch between two different branes. If several branes are stacked together, strings can connect different members of the stack. The possible string states then carry information about the branes they connect. At low energies, these open string states can appear as particles and fields living on the brane. That connection became one of the most important developments in modern string theory. A brane is not simply sitting there providing scenery. It can carry charge, it can interact, it can support excitations. Several branes can form bound states, and when enough of these ingredients are combined in the right way, their gravitational description can begin to look like a black hole. This is the point where our earlier discussion of black hole entropy returns. Remember the puzzle? A classical black hole looks remarkably simple from far away. Mass, charge, and angular momentum tell us most of what an external observer needs to know about a stationary black hole in the usual setting. Yet its enormous entropy says there must be an enormous number of microscopic states corresponding to the same macroscopic object. String theory needed to show us what those states could actually be. D-branes provided a way to do that. One especially important example begins in Type 2 B-string theory. We have already encountered the slightly inconvenient fact that superstring theory naturally uses 10 space-time dimensions. To make contact with a lower dimensional world, some spatial directions can be compactified. For the system we're interested in, physicists often consider several compact directions. One is a circle, usually called S1. 4 more can be packaged into a compact 4-dimensional space, often taken in simplified examples to be a 4-dimensional torus called T4, although another space called K3 can also be used in related constructions. Don't worry about trying to visualize all of this at once. The circle is manageable. The 4-dimensional torus is where the imagination begins requesting annual leave. What matters is that these compact directions provide places for branes to wrap. Suppose we introduce D1 branes. A D1 brane has 1 spatial dimension. We can wrap it around the compact circle. If you were able to look only at the non-compact large dimensions, you would not see a long brane stretching away indefinitely. Its extended direction is wrapped around a tiny compact loop. Then introduce D5 branes. A D5 brane has 5 spatial dimensions. We can arrange each D5 brane so that it wraps the same circle as the D1 branes, and also wraps the 4 compact directions of the T4. Now we have 2 kinds of branes sharing 1 common direction. The D1 branes lie along the circle, the D5 branes lie along the circle, and extend through the 4 compact dimensions as well. From the viewpoint of the remaining large spatial dimensions, this entire arrangement can appear localized. We call it the D1 to D5 system. That name may not have the immediate charm of Fuzzball, but it has the advantage of telling you exactly which branes have turned up. Suppose there are many D1 branes and many D5 branes. These are not simply independent objects passing one another politely. Open strings can stretch between them. Some strings have one endpoint on a D1 brane and another on a D5 brane. Others connect branes within the same stack. The combined system has a large collection of possible quantum excitations. Under suitable conditions, the D1 branes and D5 branes form a bound state. And that bound state is enormously important because its microscopic states can be studied using methods that are far more controlled than trying to examine the interior of a fully formed black hole directly. There is also a useful role played by supersymmetry. Certain configurations of branes preserve part of the supersymmetry of the underlying theory. States with this special property are often called BPS states. The initials come from Bogomolny, Prasad and Summerfield, 3 physicists whose names are now quietly carried through an impressive amount of theoretical physics. BPS states have special mathematical protection. Certain properties, including quantities related to state counting, can remain unchanged as we vary the strength of interactions. That gives physicists a clever route between 2 descriptions. At weak gravitational coupling, the system can be studied as strings and branes. Gravity is mild enough that counting the microscopic states can be manageable. Then we can imagine increasing the coupling. The objects interact more strongly gravitationally. Eventually, the macroscopic description can become black hole-like. If the relevant protected state count does not change along the way, we can compare the number obtained in the weakly coupled string description with the entropy calculated from the corresponding gravitational object. This is roughly the strategy behind the famous microscopic entropy calculations that transformed black hole physics in the 1990s. It is worth appreciating how unusual this is. Suppose I give you a black box and tell you that it contains an enormous number of possible microscopic arrangements. Unfortunately, whenever you open the box strongly enough to examine what is happening inside, the contents collapse into something you cannot calculate. That would be inconvenient. String dualities and supersymmetry sometimes let physicists change the conditions until the system becomes easier to analyze, count the states there, and then relate the result back to the strongly gravitating regime. It is as though the black box comes with a second setting labelled same essential state count considerably less impossible. Physicists appreciate those settings. The D1 to D5 system alone already has a rich collection of states, but an especially important black hole appears when another ingredient is added: momentum. The D1 branes and D5 branes share the compact circle. Excitations can carry momentum along that direction. We usually call this third charge G for momentum. Now the system becomes D1-D5-P, D1 charge, D5 charge, momentum charge. In 5 non-compact space-time dimensions, suitable configurations carrying these 3 charges can have the macroscopic description of a black hole with a finite horizon area. This 3-charge system became one of the central laboratories for microscopic black hole physics. Why 3 charges? Because the 2-charge and 3-charge cases behave differently in the simplest classical descriptions. The 2-charge D1 to D5 system is extremely useful for understanding microstates, but the corresponding naive classical geometry does not give the same sort of finite area macroscopic horizon as the 3-charge black hole. Adding momentum produces the famous 3-charge setup whose entropy can be directly compared with a black hole of non-zero horizon area. That distinction will matter when we start discussing explicit microstate geometries. It prevents us from casually treating every D1 to D5 configuration as though it were already an ordinary large black hole. The microscopic picture can be described in several duality-related ways. One particularly useful description turns the D1 to D5 bound state into something behaving like an effective long string. This does not mean that all the branes literally melt into one piece of ordinary string. It means that the low-energy excitations of the bound system can be organized using a 2-dimensional conformal field theory, often shortened to CFT, whose states can be thought of in terms of effective strings with different winding structures. Here the word winding becomes important. A string can wrap around a compact circle once, or twice, or many times. If it winds many times, its effective length can become much greater than the circumference of the circle itself. Imagine a racetrack with a tiny circumference. Running one lap gives you a short path. But if someone insists that the route consists of 1,000 laps before you are allowed to stop, the effective course has become considerably longer. The circle has not grown. The amount of string wrapped around it has. This allows excitations on a multiply wound object to have much smaller energy spacings than you might expect from the size of the compact circle alone. That effect is related to what string theorists call fractionation. It becomes important when trying to understand how microscopic stringy objects can produce structure on scales much larger than the fundamental string length. This is one of the conceptual steps that makes fuzzballs possible. At first, the idea of using strings to modify a black hole horizon may seem hopeless. A fundamental string is supposed to be fantastically small. An astrophysical black hole can be kilometers or millions of kilometers across. How could microscopic strings possibly matter across something so large? The answer is not that one tiny string suddenly inflates like a balloon. The answer involves enormous bound states, large winding numbers, many degrees of freedom, branes, charges, momentum, and collective effects. The relevant object is not one isolated string. It is a complicated quantum state built from many interacting ingredients. Collective systems frequently behave on scales very different from the scale of their basic components. A water wave can stretch for meters, even though individual water molecules are tiny. A crystal can fill your hand, even though the atoms inside it are microscopic. A storm can cover hundreds of kilometers, even though no individual air molecule is remotely storm-sized. Those analogies are not descriptions of fuzzballs, but they help remove one misleading instinct. Microscopic building blocks do not force every collective structure they create to remain microscopic. String theory adds another useful feature. Branes can carry several kinds of conserved charge, and through dualities, the same physical system can be rewritten in apparently different ways. A configuration described as D1 branes and D5 branes in one duality frame might be related to a description involving fundamental strings and momentum in another. This is not merely changing the names on the objects. different descriptions make different aspects of the same underlying physics easier to see. For example, consider a string wrapped many times around a compact circle while carrying a travelling wave. The shape of that wave can vary. The string can trace different profiles in the non-compact dimensions. Different profiles represent different microscopic states. Through string dualities, such configurations can be mapped into D1 to D5 states. This became a powerful way to construct explicit geometries corresponding to individual microstates. Now we're approaching the first hint that the old black hole picture may be too coarse. If several microscopic states all have the same total charges, then from far away they can look very similar. A distant observer measures the total D1 charge, the total D5 charge, perhaps momentum, perhaps angular momentum. Those large-scale measurements do not reveal every detail of how the underlying strings and branes are arranged. This is exactly what we need if these configurations are going to behave like black hole microstates. One macroscopic description, many microscopic possibilities, but move closer, at least in examples where we can calculate the geometry explicitly and differences can appear. The detailed string or brane configuration affects how the geometry ends. Two states that look almost identical from far away need not remain identical everywhere. That is a major departure from the simplest classical intuition. In the traditional black hole picture, we begin with a geometry containing an event horizon, and then ask where the microscopic states are hidden. In the string theory approach, we can sometimes begin with a specific microscopic state, and ask what geometry that individual state produces. Those are not the same procedure. Imagine being shown a glass jar from a kilometre away. At that distance, every jar of the same shape and mass looks identical. You might develop a perfectly good large-scale description based on the total mass and dimensions. Then someone hands you binoculars. One jar contains rice, another contains beads, another contains tiny folded pieces of paper. The coarse description was not wrong. It simply averaged over details you could not resolve from far away. Black hole microstate research asks whether something similar may happen with classical geometry. Perhaps the smooth black hole is a coarse description of many underlying quantum states. The comparison should not be pushed too far. A fuzzball is not a container filled with little pieces of string. There may not be a separate classical container at all. The geometry itself is part of the state. That subtlety is important. In general relativity, matter tells space-time how to curve, and space-time influences how matter moves. In string theory, the distinction can become even more entangled, because the extended objects, fields, fluxes, topology and geometry participate in one combined solution. This brings us to another object that helped bridge simple brane configurations and more elaborate microstate geometries, the supertube. A supertube is a bound state configuration in which charges and angular momentum can support an extended tubular shape. The name sounds like a particularly enthusiastic water slide, but supertubes are serious solutions in string theory. They showed that collections of branes carrying certain charges could expand into larger extended configurations rather than remaining collapsed into a point-like source. A system whose basic constituents look lower dimensional can develop what is sometimes called a dipole charge and spread into a higher dimensional shape. That possibility matters because it demonstrates, in a controlled setting, that brane-bound states do not always sit obediently where naive intuition would place them. Charges can combine. Momentum and angular momentum can support extended structure. Dualities can turn one description into another. What looked like a collection of branes located at one place can acquire a much larger geometric profile. Later work generalized these ideas into increasingly complicated microstate geometries, involving non-trivial topology and fluxes. Some solutions contain cycles through the geometry supported by flux. Instead of placing a singular brane source at a point, the charges can be represented through smooth geometric and field configurations. This is one route by which a geometry that initially seems destined to develop a singularity can instead end smoothly in a complicated structure. Again, we have to keep the scale of the claim under control. Physicists have constructed important families of smooth and horizonless solutions corresponding to particular supersymmetric black hole microstates. That does not mean every possible microstate of every realistic black hole has been written down. It certainly does not mean we can take the black hole at the centre of our galaxy, open a notebook, and draw the exact arrangement of every string inside it. The known constructions tend to live in highly controlled settings, where supersymmetry and special charges make the mathematics manageable. Real astrophysical black holes are not expected to sit quietly in exactly those idealized states. But these examples demonstrate something that was once far from obvious. String theory is capable of producing gravitational configurations with the same conserved quantities as black hole-like systems, while possessing detailed structure that the simplest classical geometry does not display. This makes the entropy counting more tangible. Remember what entropy is asking us to count. If a macroscopic black hole corresponds to an enormous number of microscopic states, we should not imagine one classical geometry somehow wearing an invisible badge saying, contains e to the s possible configurations. Ideally, we want to understand what distinguishes those configurations. In the D1 to D5 description, states can differ through the ways effective strings are wound and excited. Different component strings can have different lengths. Different excitations can be placed on them. Angular momentum can be distributed differently. With momentum included, left-moving and right-moving excitations can contribute in different ways depending on the state. From the microscopic viewpoint, the number of possibilities becomes enormous. From far away, many of them share the same total charges. This is exactly the relationship between microstate and macrostate that black hole thermodynamics had been hinting at. There is another important idea hiding here. If black hole microstates are genuinely different physical states, then information has somewhere to reside before we even discuss Hawking radiation. A particular collapsing quantum state does not have to disappear into a featureless object characterized only by mass, charge, and spin at the fundamental level. Its microscopic details can, in principle, be encoded in which string theory microstate is produced. That alone does not solve the information paradox. We still need to know whether radiation can carry those distinctions back out. We still need to understand what happens near the place where classical general relativity predicts the horizon. We still need to explain why an observer far away sees something that behaves so much like an ordinary black hole. And we still have the difficult question of what an infalling observer experiences. But the problem has changed. We're no longer asking quantum information to survive inside a theory that gives us only one featureless macroscopic black hole. We have an enormous space of possible microscopic configurations. The next question is where their differences live. This is where the early D1 to D5 geometries became especially provocative. Researchers constructed geometries associated with specific two-charge states, and found that the geometries could agree with the expected black hole-like form over a large region. An observer travelling inward could enter a long gravitational throat. From far away, the state could therefore resemble the beginning of an ordinary black hole geometry, but the throat did not necessarily continue into the same horizon, and singular interior expected from the naive classical solution. Different microstates could end differently. The detailed state determined the structure near the end of the throat. That is precisely the sort of behaviour the old picture had not prepared us for. Far away, the differences are difficult to see. Closer in, they matter. If we deliberately ignore the differences among a huge collection of individual states and replace them with one average description, a familiar black hole-like geometry may emerge as the coarse result. But an individual quantum state need not be identical to that average. This distinction between an individual microstate and a coarse-grained black hole will keep returning. It is easy to lose because everyday thermodynamics trains us to treat the smooth average as though it were the object itself. A cup of tea has a temperature, even though no individual molecule possesses the temperature of the whole cup. Pressure is useful, even though a single molecule does not carry a tiny pressure gauge. Thermodynamic quantities emerge when we stop following every microscopic degree of freedom. Black hole geometry may contain a similar lesson, though in a much more radical form. The horizon that appears in the course description could be telling us what happens when we ignore the precise microscopic state. Then the individual states may contain structure, where the average description gives us a smooth horizon. This is not yet enough to say that a black hole is a fuzzball. There are different versions of the microstate program, different levels of what has been explicitly constructed, and ongoing debates about how representative known geometries are of typical black hole states. But we now have the ingredients that make the proposal intelligible. We have strings that can carry excitations. We have d-branes carrying conserved charges. We have compact dimensions around which strings and branes can wrap. We have momentum travelling along shared directions. We have bound states with enormous numbers of microscopic arrangements. We have supersymmetry protecting quantities that allow state counts to be compared across different regimes. We have dualities giving us alternative descriptions of the same system. We have extended configurations such as supertubes showing that brane-bound states can spread into larger structures. And we have explicit examples where different microscopic states produce different gravitational geometries, even though they resemble the same black hole-like object from sufficiently far away. Now the word fuzzball becomes less mysterious. The fuzz is not an extra substance poured into an otherwise ordinary black hole. It is not something placed around the singularity after the classical geometry has already formed. The fuzzball proposal says that an individual black hole microstate should not be pictured as the familiar classical black hole with a smooth event horizon, a mostly empty interior, and a singularity waiting somewhere deeper inside. Instead, the microscopic string theory degrees of freedom form a complicated configuration that occupies roughly the region we would normally associate with the black hole. There is structure there. Strings can be wound, branes can be wrapped, fluxes can support non-trivial geometry. Different microstates can contain different arrangements of these ingredients. The geometry can develop a long throat that looks very much like the exterior of an ordinary black hole, but instead of continuing through a conventional horizon into an empty interior, the geometry eventually caps off in a state-dependent way. That is the essential fuzzball idea. The black hole is not a hollow region with all of its interesting physics hidden at a tiny point in the middle. The structure is spread through the would-be black hole region itself. Calling it a fuzzball can make this sound more material than it really is. You should not imagine a black sphere covered in hair. There is no enormous wad of cosmic wool floating where the event horizon used to be. And despite the name, nothing in the theory requires the object to feel soft, which is fortunate because testing that experimentally would involve an unfortunate research proposal. Fuzz refers to complicated quantum structure. The important distinction is between a classical geometry that remains smooth through the horizon and a microscopic state whose stringy structure prevents that conventional horizon and interior geometry from existing in the same way. Start far away from the object. At a large distance, a fuzzball with a given mass, charge and angular momentum should produce almost the same gravitational behavior that we would associate with the corresponding black hole. That has to be true. If it behaved completely differently from far away, it would not be a useful candidate for a black hole microstate. A planet orbiting at a safe distance should not suddenly notice that someone changed the microscopic description. Light passing far from the object should respond mainly to its total mass and other macroscopic properties. The familiar exterior geometry remains a very good approximation over a large region. Move inward, however, and eventually the details of the state matter. For some explicitly constructed string theory microstates, the space-time develops a deep throat. The deeper you travel into that throat, the more the geometry resembles the region outside a black hole. If you ignored the detailed microstate and continued using the coarse classical solution, you would expect to reach an event horizon. But the individual microstate geometry does something else. It caps off. Different states can cap off differently. The detailed arrangement of strings, branes, fluxes, angular momentum, and topology determines what happens there. This gives us an important way to think about the relationship between a fuzzball and an ordinary black hole. The classical black hole may be a coarse-grained description. A fuzzball is intended to represent an individual microscopic state. We've already seen this distinction in more familiar physics. Suppose someone gives you a container of gas. At the macroscopic level, you might describe it using temperature, pressure, and volume. Those few numbers are extremely useful. You do not need to know the position and velocity of every molecule every time you want to decide whether the gas is hot. But the gas is not fundamentally made from temperature. Temperature is a collective description of an enormous number of microscopic degrees of freedom. Many different molecular configurations can give you the same temperature and pressure. If you average over those configurations and ignore the details, you get a smooth thermodynamic description. The fuzzball proposal suggests something similar, though much more dramatic, may happen with black holes. Mass, charge, angular momentum, horizon area, and temperature give us a macroscopic description. Underneath that description may be an enormous number of distinct quantum states. If we average over them, or if our experiment cannot resolve their microscopic differences, the result can look like the familiar black hole. But an individual state need not literally contain every feature of that average geometry. In particular, it need not contain the conventional smooth horizon, followed by an independent empty interior. This is easy to say and difficult to accept, because the event horizon has become so central to the way we think about black holes. Take away the horizon, and it sounds as though we have taken away the black hole. That depends on what we mean by black hole. If we mean the exact classical solution of general relativity, then yes, replacing the smooth event horizon with horizon-scale quantum structure is a major change. If we mean an object that, from far away, is extremely compact, gravitationally powerful, dark, and capable of reproducing the thermodynamic behavior associated with black holes, then a horizonless microscopic description may still reproduce much of what distant observers call a black hole. The difference only becomes obvious when we ask questions that depend on the microscopic structure. Information is exactly that kind of question. In the old picture, matter crosses the horizon. Once it is inside, its detailed information is inaccessible to the outside. Hawking radiation is produced in a way that appears almost independent of the detailed state of the infalling matter. The black hole eventually evaporates. Then we have the information paradox. A fuzzball changes the sequence at the crucial step. There is no ordinary empty horizon through which information simply disappears into an inaccessible interior. Instead, incoming matter encounters the degrees of freedom of the fuzzball. Its energy and quantum information become part of the state of that complicated object. Radiation can then be produced by the fuzzball's microscopic degrees of freedom, and because the emission can depend on the specific state, the radiation can carry information. That sounds simple when stated in a few sentences. It is anything but simple in the mathematics. Still, the conceptual change is very clear. A normal hot object can radiate information because its surface contains degrees of freedom. Imagine heating a lump of coal. It emits radiation. The exact radiation from a particular microscopic state is not fundamentally detached from the state of the coal. A black hole in Hawking's original semi-classical calculation behaves differently because the horizon is locally vacuum-like. There is no ordinary material surface storing and processing the information there. The radiation appears thermal because it is associated with quantum fields around a smooth horizon rather than with a conventional information-carrying surface. The fuzzball proposal removes that vacuum horizon from the fundamental microstate. The object has structure instead. This does not mean fuzzball radiation has to look obviously non-thermal. That would create an immediate observational problem. Large black holes behave thermally to an excellent approximation. The radiation from a generic, complicated quantum state can look thermal in coarse measurements, while still containing extremely subtle correlations that preserve information. That is an important distinction. Looks thermal does not necessarily mean contains no information. A burning piece of paper produces radiation that looks extremely ordinary if you only measure broad properties such as its spectrum and total power. But at the full quantum level, the outgoing particles can contain correlations with the microscopic state of the system that emitted them. You are unlikely to reconstruct the original shopping list from those correlations. Quantum mechanics does not promise a practical recovery service. It only requires that fundamental information not be destroyed. This is what fuzzballs are designed to allow. Different microstates can radiate differently at the microscopic level. The exact state matters. Information does not need to cross an empty horizon and wait for a miracle later. It remains part of the physical degrees of freedom capable of interacting with the outside. There are explicit examples where special non-extremal microstate geometries emit radiation in a way that matches calculations performed using the corresponding microscopic description. These examples are not a complete model of generic astrophysical black hole evaporation, but they show that horizonless string theory microstates can produce information-carrying radiation rather than requiring the standard Hawking pair creation story at a smooth horizon. That gives the fuzzball proposal something more than a philosophical advantage. There are actual systems in which the microscopic and gravitational descriptions can be compared. The next obvious question is what the surface of a fuzzball looks like. Unfortunately, surface is another word that can lead us in the wrong direction. A planet has a surface because rock or gas reaches some physical boundary. A neutron star has matter all the way to its outer layers. A fuzzball need not possess one simple, rigid surface located at one exact radius. Different microstates can have different geometries. The transition from the black hole-like throat to the detailed stringy region can be complicated. In some examples, smooth geometry and flux replace what would have been a singular source. In others, genuinely string-scale or quantum ingredients may be essential. So it is safer to think of a fuzzball as possessing state-dependent structure in the region where the classical black hole description would have placed its horizon and interior. The proposal is broader than any one neat picture of a shell. This also helps explain why the word ball should not be taken too seriously. A rotating black hole is not described by perfect spherical symmetry. Individual microstates can have complicated shapes and multipole structures. The microscopic geometry may be anything but a featureless ball. Fuzzball is simply the name that survived. Physics has many examples of terminology that becomes permanent before anyone has time to choose something more dignified. Quarks come in flavors. They also carry colors. Black holes can have hair. String theory has brains. At this point, fuzzballs are hardly the strangest thing on the menu. One particularly important claim of the fuzzball program is that the structure can extend to the scale associated with the would-be horizon. This is much larger than the tiny region near the classical singularity where people might naturally expect quantum gravity to become important. That is the radical step. Why should quantum effects matter there? For a very large black hole, the curvature at the horizon can be weak. Nothing in ordinary local geometry announces that we have reached the place where quantum gravity must take over. General relativity seems perfectly comfortable. Yet the information paradox tells us that leaving the horizon completely unchanged creates a problem. If outgoing Hawking quanta continue to be produced through the ordinary entanglement pattern at a smooth horizon, small corrections are not enough to restore the missing information. The state has to differ substantially from the traditional vacuum horizon picture. Fuzzballs take that conclusion seriously. Instead of saying that quantum gravity only repairs the singularity after information has already disappeared behind the horizon, the proposal says that the enormous number of available black hole microstates changes the physical state on the scale of the black hole itself. This does not mean quantum gravity becomes strong everywhere around us whenever a black hole is nearby. The exterior can remain extremely well described by ordinary semi-classical gravity. The difference appears in the region where the classical solution would have continued into the horizon and interior. An observer standing far outside does not need to abandon Einstein's equations. The correction is associated with what the black hole is microscopically. There is another way to understand why this might be possible. Black holes have enormous entropy. The number of possible microscopic states associated with a black hole is roughly exponential in that entropy. That means there are not merely 10 possible fuzzballs, or 10,000, or even a number that would fit politely into an ordinary sentence. There should be an extraordinary number of states. If the black hole entropy is S, the number of microscopic states is of order e to the s. For a macroscopic black hole, that is enormous beyond ordinary intuition. The existence of such a huge space of states can make collective quantum effects important even when the amplitude associated with any one particular transition seems extremely small. In fuzzball discussions of gravitational collapse, this has motivated the suggestion that a collapsing shell should not simply continue into one classical black hole interior. Instead, the quantum state may spread over the enormous space of available fuzzball states. A transition into any one specific fuzzball configuration could be strongly suppressed, but the number of possible final fuzzball states is enormously large. The competition between tiny amplitude and huge degeneracy is part of the proposed mechanism. This aspect of the picture is less directly established than the explicit construction of special microstate geometries, so it is worth keeping the distinction clear. We have concrete families of string theory microstates. We have entropy counts. We have special horizonless geometries. We have explicit emission calculations in some cases. A complete dynamical description of realistic stellar collapse into a generic fuzzball state remains a much harder problem. The proposal is trying to tell us what the endpoint of quantum gravitational collapse should be, but we do not yet possess a movie of an ordinary star collapsing frame by frame into a fully realistic fuzzball. The difference matters because theoretical physics can sometimes make a very persuasive map before it has built every road on the map. This is also why statements such as string theory proved that black holes have no horizons go too far. It has not. The fuzzball program argues that individual black hole microstates in a full quantum gravity description should be horizonless and possess structure replacing the traditional interior. There is substantial evidence for this idea in controlled string theory systems. There are also open questions about generic states, non-supersymmetric black holes, realistic astrophysical collapse, and the precise relation between microstate geometries and the full set of quantum states. Even within string theory, researchers use several related approaches to black hole microphysics. The field has not reduced the entire subject to one universally accepted drawing, labelled, "This is exactly what every black hole contains." That uncertainty does not make the idea uninteresting. Quite the opposite. Fuzzballs became important because they offer a very concrete answer to a question that the old black hole picture left unanswered. What does a black hole microstate look like? The answer is not exactly like every other microstate, with all differences hidden somewhere we cannot describe. The answer may be that each state is a different quantum configuration of extended objects, fields, fluxes, and geometry. The common classical black hole emerges only after we ignore those differences. This brings us back to the horizon. Suppose you have an enormous collection of microstates. Each one differs in complicated ways near the would-be horizon scale. If you average over them, the details disappear. The average description can become smooth and simple. A horizon can appear in that coarse description even if an individual state does not possess a conventional horizon. Again, ordinary thermodynamics gives us a rough analogy. A photograph of a crowd taken from very far away might look like one smooth patch of colour. Zoom in and you find thousands of individuals. The smooth patch was a useful description at low resolution. It did not mean each person was literally made from a continuous field of average-coloured material. With fuzzballs, the stakes are higher, because the thing that may emerge only after coarse graining is space-time geometry itself. The classical interior could be part of an effective description rather than a literal region, shared by every exact quantum microstate. That idea is difficult because we normally treat space-time as the stage on which physical states exist. String theory and quantum gravity keep suggesting that the stage may itself be part of the performance. Geometry can depend on the quantum state. Topology can change between descriptions. Objects that appear gravitational in one formulation can appear as collections of brains in another. The clean separation between what space-time is and what is sitting inside space-time becomes less reliable. A fuzzball makes that problem impossible to ignore. It is not ordinary matter placed inside a pre-existing black hole volume. The stringy state helps define the geometry. Remove the microstate and replace it with the averaged classical solution, and you may create an interior that was not present in the same way in the exact state. That is why saying that a fuzzball fills the inside of a black hole is useful only as a first approximation. It sounds as though the ordinary horizon remains where it always was and someone has packed the interior with strings. The stronger proposal is different. There is no ordinary horizon separating an exterior from a separate empty interior. The state itself occupies the region and ends the geometry. What we called the interior belonged to the classical approximation. This immediately raises a slightly alarming question. What happens if you fall toward one? In ordinary general relativity, a sufficiently large black hole can have a horizon where the local tidal forces are mild. You should cross without noticing anything special at that exact moment. If a fuzzball has real structure there instead, shouldn't you hit it? Does the peaceful horizon become a violent surface? Would you bounce, burn, become part of the fuzzball? And if the answer is that something dramatic happens, how could general relativity have worked so well? Those questions lead into fuzzball complementarity and the broader arguments about what an infalling observer experiences, but they are best handled separately. For the moment, there is a more immediate issue to settle. We have been talking about an enormous number of fuzzball states, as though we can simply place them in a very large catalogue. But that number is not decorative. It is the core of the black hole's entropy. If one macroscopic black hole can correspond to an astronomical number of distinct microscopic configurations, then understanding those microstates is what tells us where the information can be stored and why the black hole has the thermodynamic properties it does. So the next step is not to ask what one fuzzball looks like. It is to ask why there must be so many of them, how different states can share the same mass and charges, and how an object that appears almost featureless from far away can secretly possess more possible quantum configurations than almost anything else in nature. Write down the mass of a black hole. Then, if it is rotating, write down its angular momentum. If it carries electric charge, write that down too. You have now recorded almost everything the traditional stationary black hole lets the outside universe easily know about it. That is remarkably little information for an object that might have formed from an entire star. Before the collapse, the star contained an enormous number of particles. Those particles could occupy different quantum states. They could have different arrangements, motions, correlations, and histories. The star might have rotated slightly faster in one region than another. Its magnetic field could have been tangled in countless ways. Different atoms could have occupied different positions. Change those microscopic details and you have a different physical state. Yet after the system forms a stationary black hole, many of those differences seem to disappear from the simple external description. Two black holes can have the same mass, the same charge, and the same angular momentum even though they were created from completely different collections of matter. This is where the idea of a microstate becomes essential. A microstate is one specific microscopic configuration consistent with a particular macroscopic description. We use this idea throughout statistical physics. Consider a box filled with gas. You might describe the gas by saying that it has a certain temperature, volume, and pressure. Those are macroscopic properties. They tell you what the gas looks like when you stop trying to follow every molecule individually. But there are unimaginably many microscopic arrangements that can produce the same temperature and pressure. One molecule might be near the left side of the box in one microstate, and near the right side in another. Another molecule might be moving upward instead of downward. Change the positions and momenta of the particles while keeping the large-scale quantities effectively unchanged, and you move from one microstate to another. From across the room, nothing appears to have happened. The thermometer still shows the same temperature. The pressure gauge still gives the same reading. Microscopically, however, the state is different. Black hole entropy tells physicists that something similar must be happening with black holes. The surprise is the scale of it. Black holes possess a quantity called Bekenstein-Hawking entropy, related to the area of the event horizon in the classical description. In units where the constants are arranged conveniently, the formula is often written as the entropy being equal to 1/4 of the horizon area measured in Planck units. The important point tonight is not the factor of 1/4, it is what entropy means. In statistical mechanics, entropy is related to the number of microscopic states compatible with the macroscopic description. If we call that number of states omega, then entropy is essentially the logarithm of omega. Turn that statement around and the number of states grows exponentially with the entropy. So when a black hole has a huge entropy, the number of possible microstates is not merely huge in the ordinary sense, it is exponential in something that is already enormous. For a black hole with roughly the mass of our Sun, the dimensionless Bekenstein-Hawking entropy is of order 10 to the 77th. That does not mean there are 10 to the 77th microstates. That would already be an absurdly large number. The number of states is roughly the exponential of a number of that scale. Trying to write it out in full would be a questionable use of both paper and the remaining lifetime of the universe. This enormous count immediately changes the way we should think about a black hole. The macroscopic object looks simple because many microscopic differences have been ignored. Mass tells us one thing, charge tells us another, angular momentum tells us another. But those few quantities do not specify the complete quantum state. The same macroscopic values can correspond to an enormous number of different underlying states. This is not an optional decoration added by Fuzzball researchers. The entropy itself demands microscopic degeneracy of some kind if black hole thermodynamics has the same statistical meaning that entropy has elsewhere in physics. The difficult part is identifying what those states actually are. Before string theory provided examples, physicists could write down the entropy formula without possessing a detailed microscopic catalogue. It was rather like being told that a hotel contains an astronomical number of rooms while being shown only the front desk. You know the rooms must be accounting for something. You would quite like to see a floor plan. String theory began providing pieces of that floor plan. In the D1 to D5 and related systems we encountered earlier, the same large-scale charges can arise from many different quantum configurations. The effective strings can have different winding structures. Excitations can be distributed differently. Momentum can be divided among available degrees of freedom in different ways. Angular momentum can be carried by different parts of the state. The microscopic arrangements differ even when the total charges measured from far away remain the same. That is exactly the structure we need. One macrostate, many microstates. The famous Strominger-Vafa calculation made this relationship quantitative for a special class of supersymmetric 5-dimensional black holes. They considered a string theory system built from d-branes and momentum, counted the degeneracy of suitable microscopic states, and found that the logarithm of that count reproduced the Bekenstein-Hawking entropy of the corresponding black hole. This was a major result because the area formula was no longer only a mysterious thermodynamic rule. At least for those black holes, physicists could point to actual quantum states and say, in effect, these are the things being counted. The agreement was not obtained by inventing the number of states to match the black hole. The microscopic counting was performed using the string theory description, while the macroscopic entropy came from the gravitational horizon area. The two calculations used very different languages. They met at the same answer. That gave strong evidence that the entropy of those black holes really does count underlying quantum states. But counting states and describing states are not quite the same task. Suppose I tell you there are 10 million possible arrangements of objects inside a warehouse. That tells you something important about the warehouse. It does not tell you what arrangement number 4,728,331 actually looks like. The same distinction appears in black hole physics. A successful entropy calculation can show that the required number of microstates exists without giving a simple space-time geometry for every one of them, and this becomes particularly important when discussing fuzzballs. Some microstates can be represented by explicit smooth or controllable geometries. Researchers can calculate the fields, charges, and shape of those configurations and see how they differ from one another. These examples are extremely valuable because they show directly that two states with the same asymptotic black hole charges need not be identical near the would-be horizon, but the known smooth microstate geometries should not automatically be assumed to represent every state, contributing to the full black hole entropy. The typical microstate of a large black hole may be much more quantum and much less easily represented by one smooth classical geometry. That distinction prevents us from imagining a fuzzball as simply one of several attractive geometric sculptures sitting inside a catalogue. The full space of states is much larger and likely contains configurations for which ordinary geometric language becomes insufficient. Still, the examples teach us something basic. Macroscopic sameness does not require microscopic sameness. Imagine looking at a city from an airplane at night. You can measure its total electrical consumption. You can count roughly how much light it produces. You might estimate its population. 2 evenings could produce nearly identical totals, yet inside the city completely different things are happening. One apartment contains someone cooking dinner, another contains someone watching television. A hospital is operating, a restaurant is closing, someone has lost their keys, someone else has found keys that are almost certainly not theirs. The large-scale measurements do not specify the detailed state of the city. A distant measurement of a black hole has a similar limitation, although the underlying physics is very different. Mass, charge, and angular momentum give us coarse information. They do not identify which quantum microstate we have. This is why the apparent simplicity of a black hole is not necessarily evidence that its microscopic structure is simple. Quite the opposite may be true. The simplicity can be a consequence of coarse graining. Coarse graining means deliberately ignoring microscopic details and describing only larger scale properties. We do it constantly. When you say a cup of tea is warm, you do not list the quantum state of every water molecule. When a weather report says the air temperature is 20 degrees, it does not describe the position of every nitrogen molecule over London. That would make the evening forecast somewhat longer. Instead, we keep the information relevant to the scale we care about and ignore the rest. Black hole thermodynamics may be doing something similar. The classical black hole geometry could be the large-scale description that results when we stop distinguishing among enormous numbers of microscopic quantum states. From far away, those states share the properties that determine the gravitational field. Closer to the would-be horizon, their differences may become important. This makes the classical event horizon an especially interesting object. If all the exact microstates were completely identical outside and at the horizon, their distinguishing information would have to remain somewhere deeper inside. That returns us to the traditional picture and its information problem. The fuzzball proposal instead suggests that the distinctions among the states can extend through the region where classical general relativity would have given us the horizon and interior. The macroscopic black hole is then like an average description of many different underlying configurations. An average can have properties that none of its individual members possesses in exactly the same form. Take several photographs of a moving person and average the images together. The result may contain a blurry figure. The blur is real as an average, but there was never one person whose body was literally spread evenly through every blurred position at the same time. Something loosely analogous can happen when microscopic states are replaced by a coarse description. A smooth classical geometry might capture what typical measurements see without being a literal description of every exact state at every location. That possibility helps explain how fuzzballs can differ microscopically, while preserving familiar black hole behavior at large distances. The exterior gravitational field does not need to reveal every detail. Most details can be hidden in very fine structure. This is also why the word hair keeps appearing in black hole discussions. The classical no-hair idea says that stationary black holes in the standard setting are characterized externally by only a small number of conserved quantities. Microstates seem to require vastly more distinctions than that. So where is all the extra information? In a quantum theory, it does not need to appear as a large classical label that you can measure with an ordinary telescope. Different quantum states can share the same expectation values for simple macroscopic observables. Their differences may appear only in complicated correlations or very fine measurements. Think about two enormous documents containing different text, but exactly the same number of pages, the same weight, and the same dimensions. A bathroom scale cannot tell them apart. That does not mean the documents contain the same information. You're simply using an observable that is insensitive to the relevant details. This same logic is important for black holes. When we say that two microstates have the same mass and charges, we're not saying the states are identical. We are saying those particular measurements do not distinguish them. A sufficiently detailed quantum description can. This leads directly back to information preservation. Suppose one collapsing system produces microstate A and another produces microstate B. They have the same total mass. They may have the same angular momentum and charge. A distant observer using only simple gravitational measurements initially treats them as the same black hole. But if A and B are genuinely different quantum states, then the information distinguishing the original collapsing matter has not automatically vanished. It can be encoded in which microstate formed. The next requirement is that the later radiation depend, however subtly, on that microstate. If A emits a state of radiation that differs in its complete quantum correlations from the radiation emitted by B, then information can be preserved even if both radiation streams look almost thermal under crude measurements. That phrase, almost thermal, matters. If you measured only the average energy spectrum, the difference might be essentially invisible. The information could live in correlations among many emitted quanta. This is common in quantum systems. A single part can look random while the complete collection remains in a highly organized pure state. Consider a simple pair of entangled quantum systems. If you inspect only one member of the pair, its outcomes can look random. Inspect the joint correlations and the larger state reveals structure. A black hole capable of unitary evaporation would have to perform a much more complicated version of this. The outgoing radiation can look thermal locally, while the complete radiation state carries the correlations needed to preserve information. The enormous number of microstates is what gives the system enough microscopic capacity to encode the many possible initial conditions. There is another subtle point. The black hole entropy does not tell us that a black hole contains a tiny computer with a fixed collection of little memory cells arranged along its horizon. That visualization sometimes helps when people discuss information density, but it should not be confused with a literal microscopic model. In string theory, the degrees of freedom may be strings, branes, flux configurations, winding modes, momentum modes, or more abstract quantum states depending on which duality description is being used. The same physics can sometimes have several mathematically equivalent descriptions. One picture may make the geometry easy to understand, another may make the microscopic state count easy to calculate. Neither necessarily gives us a set of ordinary mechanical components that could be pointed to with tweezers. What remains invariant is the number of states and the physical predictions. The state count also explains why black holes are such efficient entropy containers. For a given region, a black hole represents an extraordinary concentration of entropy. Increase the black hole's area, and its entropy increases with that area. This area scaling was one of the clues that later contributed to holographic ideas in quantum gravity, where information associated with a gravitational region can sometimes be described using degrees of freedom living in fewer dimensions. For the fuzzball discussion, we do not need to follow the entire holographic road. We only need the lesson that gravity has repeatedly refused to organize information in the way ordinary volume-based intuition might suggest. A black hole's entropy scales with its horizon area. Its microstates can be counted in certain string theory systems, and a complete description of those states appears to require quantum gravity rather than ordinary matter sitting inside a classical container. There is also a practical difficulty in trying to identify a typical microstate. The number of states is so large that most of them cannot be studied one by one. Physicists therefore use statistical arguments. This is normal. No one calculates the trajectory of every molecule in a glass of water before predicting its temperature. When the number of microscopic degrees of freedom becomes enormous, typical behavior becomes more useful than a complete catalogue. But black holes create an unusual version of this problem because we care about both levels at once. Thermodynamics tells us that coarse graining should work. The information paradox asks us not to throw away the microscopic information permanently. A successful quantum theory of black holes therefore has to explain both facts. Why does the object look simple and thermal to ordinary measurements? And how does the underlying exact state remain complicated enough to evolve unitarily? Fuzzballs attempt to answer both by separating the microscopic state from the coarse, classical geometry. At coarse resolution, you recover something black hole-like. At fine resolution, the exact state contains structure and information. The distinction becomes easier to understand if we imagine a deck of cards. Shuffle the deck thoroughly. From across the room, every shuffled deck looks almost identical. Same rectangular box, same mass, same number of cards. If I tell you only those macroscopic facts, there are an enormous number of possible card orders consistent with them. Each order is a different microstate. Now imagine that the deck somehow emitted cards one by one. If the sequence of emitted cards were completely unrelated to the original ordering, the original information would disappear. If the sequence depended on the ordering, then in principle the emitted cards could encode what the initial arrangement was. The black hole problem is vastly more complicated, but the structure of the question is similar. Does the outgoing radiation depend on the exact microstate? In the traditional Hawking calculation with a smooth horizon, it does not depend enough on that state to preserve the information. In the fuzzball approach, the microscopic structure is supposed to make the emission state dependent from the beginning, and yet there is one feature we have so far treated almost too casually. Where exactly does that structure begin to matter? From far away, the different microstates need to resemble the same black hole. Somewhere inward they become distinguishable. The classical description says that the important boundary is the event horizon. The fuzzball description says an exact state does not contain that ordinary empty horizon in the same way. Those statements leave us with a very practical question. Imagine sending something toward the object, a photon, a probe, or, for the traditional theoretical physics volunteer program, an observer. At what point does it encounter the microscopic differences? Does radiation reflect from the structure? Does matter become absorbed into the enormous number of fuzzball degrees of freedom? Can an infalling observer still experience something approximately like smooth passage through a horizon? And if the microscopic state really replaces the horizon, why did general relativity ever predict that crossing it should feel completely uneventful? Those questions move us from counting the possible states to confronting the place where the old and new pictures disagree most sharply. The edge of the object itself. Your spacecraft is already falling. There is no engine powerful enough to change the thought experiment now, so we may as well make ourselves comfortable and check the instruments. Ahead is an object with the same mass as a black hole. From far away, its gravitational field behaves almost exactly as expected. Light bends around it. Your trajectory curves inward. Signals you send back toward a distant observer become increasingly redshifted. Nothing on the approach announces in large friendly lettering that the object is a fuzzball rather than the classical black hole we discussed earlier. That similarity is essential. A proposed black hole microstate that behaved nothing like a black hole outside the would-be horizon would not explain very much. The disagreement begins only when you reach the region where ordinary general relativity tells a very specific story. According to the classical picture, if the black hole is large enough, the event horizon itself should not be a physically violent place. You do not strike a wall. You do not encounter a solid surface. You do not hear a small electronic voice announce, "You have now entered the black hole." Locally, space-time around the horizon of a sufficiently large black hole can be quite ordinary. The curvature there can be mild, and an observer in freefall can cross the horizon without encountering anything special at that exact location. This expectation is closely related to the equivalence principle and to the smooth horizon assumptions that later became central to the firewall debate. You continue inward. Only later do tidal forces become severe, depending on the black hole's size and your trajectory. The event horizon itself is not supposed to be made from matter. That is the old picture. The Fuzzball proposal removes precisely this feature. An exact Fuzzball microstate does not contain the ordinary vacuum region extending smoothly through a traditional event horizon. Instead, string theory degrees of freedom provide real microscopic structure in the would-be horizon region. In the Fuzzball program, individual microstates are horizonless and do not possess the usual black hole interior. So what happens to our unfortunate spacecraft? At the most basic level, it encounters the fuzzball. Its energy is transferred into the enormous number of degrees of freedom making up the state. The spacecraft does not simply pass through an ordinary horizon and continue through a pre-existing empty interior. There is no conventional interior waiting behind the fuzzball surface in the fundamental description. That statement sounds straightforward. Its consequences are not. If you have spent any time learning general relativity, you may immediately object. A large black hole can have extremely weak curvature at its horizon. Why should anything dramatic happen there? Quantum gravity is normally expected to become important when distances become extraordinarily small, or when space-time curvature becomes enormous. Near the classical singularity, certainly. At the horizon of a supermassive black hole, apparently not. You could cross a horizon whose radius is millions of kilometers, while the local curvature is gentler than it would be near much smaller compact objects. Replacing that apparently peaceful region with quantum structure seems to violate one of the most trusted pieces of gravitational intuition. That is why fuzzballs are not simply a different model of what sits at the center. They require the failure of the traditional smooth horizon description on a macroscopic scale. The information paradox is the reason anyone would tolerate such an outrageous proposal. If the horizon remains ordinary vacuum, Hawking's entanglement argument returns. Outgoing radiation becomes entangled in the wrong way, with degrees of freedom behind the horizon. Small quantum corrections cannot repair the accumulating entanglement, while leaving the horizon essentially unchanged. To preserve information, the microscopic state has to differ significantly from the ordinary Hawking vacuum structure near the would-be horizon. That conclusion is one of the main motivations for horizon-scale fuzzball structure. Now we reach an awkward conflict. Quantum information appears to demand that the horizon not be empty. An infalling observer appears to demand that the horizon feel empty. Both demands cannot simply be imposed without explaining how they fit together. This problem became especially sharp in 2012, when Ahmed Al-Meiri, Donald Marolf, Joseph Polchinski, and James Sully presented an argument that became known by the initials AMPS. They considered an old black hole, one that has emitted enough Hawking radiation for information to have begun emerging according to a unitary, page curve picture. Take a newly emitted Hawking quantum. If information is being preserved, that new quantum needs the appropriate entanglement with radiation that escaped earlier. But a smooth horizon requires the same outgoing mode to have the usual entanglement with a corresponding mode behind the horizon. Quantum entanglement cannot satisfy both requirements in the necessary way. AMPS argued that three appealing assumptions cannot all survive together: unitary Hawking radiation, ordinary low-energy effective field theory outside the horizon, and an uneventful horizon for the infalling observer. One possible response was alarming enough to acquire an excellent name: a firewall. Instead of finding empty space at the horizon, the infalling observer would encounter energetic excitations. The horizon would no longer be peaceful. Something there would effectively burn or destroy the observer. The firewall proposal was not introduced because physicists had suddenly become hostile toward astronauts. It emerged because sacrificing the smooth horizon seemed, to the AMPS authors, more conservative than sacrificing quantum unitarity or allowing low-energy physics to fail in even stranger ways. The idea created an immediate storm of debate. A firewall seems to violate the expectation that a freely falling observer crossing a large horizon should experience ordinary local physics. Yet preserving that expectation appears to recreate the entanglement problem. Many proposed resolutions followed. Some tried to reformulate complementarity. Some reconsidered how interior degrees of freedom should be encoded. Others developed holographic approaches in which the relation between the interior and exterior is more subtle than a simple division into independent systems. The debate remains important because it exposes exactly how difficult it is to make the black hole interior compatible with quantum information. Fuzzballs enter the argument from a different direction. They do not begin by insisting that the traditional horizon must remain empty. In fact, they already gave that up. The information carrying structure is supposed to be present at approximately the would-be horizon scale, so a fuzzball does not need to add a firewall to an otherwise ordinary black hole. The ordinary empty horizon is already absent. This makes it tempting to say that a fuzzball simply is a firewall. That is too crude. Both pictures reject the idea that every infalling observer always experiences the standard vacuum horizon in the fundamental description, but their proposed microscopic physics is not the same. A fuzzball is intended to be a specific black hole microstate built from the underlying degrees of freedom of string theory. Its structure stores information and radiates in a state-dependent, unitary way. A firewall is a more general conclusion that energetic structure may have to replace the smooth horizon in order to resolve an entanglement conflict. The fuzzball program then asks a further question. Even though the exact state has no traditional interior, could some infalling observers still experience something that is approximately described as falling through one? This is where fuzzball complementarity enters, and the word complementarity needs careful handling. Traditional black hole complementarity suggested that an outside observer and an infalling observer could use different descriptions without producing an operational contradiction. From outside, information could be absorbed, scrambled, and eventually returned by degrees of freedom associated with a stretched horizon. For the falling observer, nothing special happened at the horizon, and the observer continued inward. No single observer could access both copies of the information in a way that demonstrated illegal quantum cloning. Fuzzball complementarity makes a different proposal. There is no claim that a literal smooth interior exists underneath the exact fuzzball state, and that the observer simply slips into it. Instead, certain processes involving the fuzzball's enormous collection of degrees of freedom may admit an approximate alternative description that resembles motion through the traditional black hole interior. The approximation is expected to work only for particular kinds of probes. The distinction usually made is based on energy. A typical Hawking quantum has energy of order, the Hawking temperature, T. Those low-energy quanta are precisely the ones that must be sensitive to the details of the fuzzball state if information is going to escape. They cannot be treated as though the horizon were an information-free vacuum. Doing so would recreate Hawking's original problem, but consider an infalling object carrying energy E much greater than T. For a large black hole, the Hawking temperature is extremely low. An ordinary macroscopic observer therefore carries energy vastly larger than the characteristic energy of an individual Hawking quantum. In fuzzball complementarity, such a high-energy impact can excite large numbers of fuzzball degrees of freedom collectively. Mathur and collaborators have proposed that the resulting collective dynamics may, for suitable coarse observables, have an approximate dual description that looks like continued infill into an effective black hole interior. This is a subtle idea, so consider something more familiar. A sound wave travelling through a solid can often be described without following every atom. At the microscopic level, atoms are interacting. At a larger scale, we describe a smooth wave moving through a continuous material. The wave is not evidence that the microscopic lattice disappeared. It is an effective description of collective behaviour. Fuzzball complementarity proposes something conceptually related, although the actual physics is far more complicated. The exact degrees of freedom remain fuzzball degrees of freedom, but certain high-energy disturbances may excite them in a way whose coarse evolution can be represented using the familiar language of an interior space-time. You would not be discovering a hidden empty chamber behind the fuzzball. The effective interior would be another description of complicated dynamics taking place in the underlying microstate. This is why the question, "Do you fall through a fuzzball?" does not have a clean yes or no answer. Fundamentally, in the fuzzball proposal, you hit and become absorbed into the fuzzball degrees of freedom. There is no ordinary horizon followed by a literal classical interior, but for some high-energy processes, fuzzball complementarity conjectures that the subsequent evolution may be approximated by the experience that general relativity would describe as continued infall. That complementary description is not expected to apply to every quantum process. In particular, it cannot be applied indiscriminately to the low-energy Hawking modes, because those modes need to carry the microstate information outward. Avery, Tudory and Pum framed this distinction by arguing that probes with energy comparable to the Hawking temperature should be sensitive to the fuzzball structure, while probes with energy much greater than the temperature may admit the approximately smooth infall description. So if our spacecraft is enormous, compared with a Hawking quantum, perhaps its occupants do not immediately experience something resembling the dramatic wall imagined in the simplest firewall picture. The high-energy collision can create collective excitations before the observer has access to a simple local measurement saying, "Here is the fuzzball surface." That is the conjecture. It should not be promoted into an established prediction. Fuzzball complementarity is one of the less settled parts of the fuzzball program. There are explicit microstate constructions and entropy calculations that can be studied in detail. The experience of a generic observer falling into a generic astrophysical fuzzball is much harder. We do not possess a complete string theory calculation following a human-sized detector toward an ordinary rotating stellar black hole and reporting what each instrument reads. That would be an impressive paper. It has not been written. Even defining the exact surface can be misleading. A fuzzball does not need to resemble a rigid shell. Different microstates can have different structures. Some known microstate geometries cap off smoothly. Others may require intrinsically quantum or stringy descriptions. A typical microstate may not possess a clean classical geometry at all. So when we imagine a spacecraft striking the surface, we're using convenient language for the region where its infalling degrees of freedom encounter the microstate structure. There may be no metal-like boundary with a sharply defined altitude. And this brings us to another odd feature of falling towards such an object. From far away, escaping from the near-horizon region is extremely difficult. The enormous gravitational redshift remains. A fuzzball being horizonless does not mean that light arriving near its structure can simply bounce away and return to us as though it had struck a mirror. Photons emitted or scattered from very near the would-be horizon generally need to travel along a very restricted set of outward trajectories to escape. Much of what interacts with the object can remain trapped for a long time or become absorbed into its degrees of freedom. Calculations exploring possible observations of fuzzball-like surfaces have emphasized how difficult it can be for scattered radiation from near the would-be horizon to escape to infinity. That helps explain how an object without a traditional event horizon could still look extremely dark. Horizonless does not mean bright. It does not mean easy to photograph. It does not mean that a telescope should see a neat glowing surface just inside the black hole shadow. Strong gravity can make a compact object observationally black hole-like, even when its microscopic description differs dramatically from a classical horizon. The same gravitational redshift that makes the region difficult to escape also changes how processes near the fuzzball appear to distant observers. Local dynamics can happen rapidly while distant signals arrive stretched and weakened. The exterior can therefore maintain much of the behavior we associate with black holes, even though the exact causal structure is different. Information can eventually escape because no true event horizon permanently removes it from the outside universe, but eventually escape need not mean immediately reveal itself. A fuzzball can scramble information across an enormous number of degrees of freedom and emit it through complicated correlations in radiation. You should not expect the spacecraft's flight recorder to come back 5 minutes later with a small note saying, "Here are the original atoms, alphabetized." Unitary information recovery can remain extremely indirect. There is also an important difference between what happens to a low-energy probe and what happens to a large infalling object. Send in a quantum whose energy is comparable to the fuzzball's temperature, and it probes exactly the degrees of freedom responsible for radiation and microstate structure. The traditional vacuum horizon approximation is not supposed to work there. Send in something carrying much more energy, and you significantly change the fuzzball's state. The object now has more total energy. The number of accessible microstates increases. In the fuzzball picture, the structure can respond to the infalling energy, rather than behaving like an inert wall. This response is part of why the simplest image of a fixed firewall is not quite appropriate. A firewall sounds like a permanent layer of destructive radiation through which you attempt to pass. A fuzzball is a dynamical quantum system. You interact with it. You excite it. Your degrees of freedom become incorporated into its much larger state space. The resulting system evolves. Mathure's proposed models of fuzzball complementarity specifically use these large collective excitations to motivate an approximate interior description for energetic infall, while retaining explicitly information-carrying behavior for Hawking scale modes. Whether that mechanism fully reproduces everything an infalling observer expects from general relativity remains a much harder question. For example, we would like an effective description to reproduce appropriate causal relationships. We would like it to explain the observer's local measurements. We would like it to work for long enough to recover the useful portion of classical interior physics without quietly reintroducing the information paradox. And we need to understand when the approximation fails. These are not small details. They determine whether fuzzball complementarity is a complete account of infall, or only a suggestive analogy supported in limited regimes. That is why, what happens if you fall into a fuzzball is one of the best questions to ask about the entire proposal. It forces us to separate three statements that are easily mixed together. First, an exact fuzzball microstate is proposed to have no conventional empty horizon and no ordinary classical interior. Second, an infalling object interacts with and becomes part of the fuzzball's microscopic degrees of freedom. Third, certain high-energy infalling processes may nevertheless admit an approximate complementary description that resembles continued motion through a smooth black hole interior. Those statements can coexist because the third is not claiming that the classical interior secretly existed all along. It is claiming that an effective space-time description may emerge from the collective quantum dynamics. If that sounds strange, it should. We are asking whether space inside a black hole could work somewhat like temperature in a gas, enormously useful at the appropriate scale, despite not being one of the fundamental microscopic ingredients. Quantum gravity repeatedly pushes physicists toward this possibility that space-time itself may be emergent. Fuzzballs make the suggestion unusually concrete, because they replace the region we thought was empty with an enormous state-dependent quantum system. The emptiness was doing important work in the old picture. It allowed the equivalence principle to tell a falling observer that nothing special happens at the horizon. It allowed quantum field theory to define the vacuum correlations responsible for Hawking's calculation. It also produced the entanglement that led to the information paradox. Remove that emptiness and the paradox can change. But now the burden shifts. The theory must explain why the universe so often behaves as though the empty horizon were there. That is the challenge Fuzzball complementarity is trying to address. Perhaps a coarse, energetic observer cannot resolve the microstate quickly enough, and instead experiences collective dynamics well approximated by smooth infell. Perhaps low-energy quanta, which have enough sensitivity to distinguish the microstate, reveal the structure through information-bearing radiation. In that division, the same object can look surprisingly classical to one kind of probe and unmistakably quantum to another. There is nothing particularly unusual about scale-dependent descriptions in physics. A wooden table looks solid to your hand. At atomic resolution, it is mostly not a continuous solid at all. A fluid looks smooth from across the room. At molecular resolution, it consists of violently moving particles. What would be extraordinary here is that the scale-dependent quantity is not merely the material inside space-time. It is the apparent continuation of space-time itself, and that gives us something potentially observable to ask about. If fuzzballs have structure where classical black holes have horizons, even structure hidden behind enormous redshift, should there be some measurable difference? Could gravitational waves notice it? Could black hole images notice it? Could radiation or echoes reveal a surface? Or could the gravitational environment hide the microstructure so effectively that an astrophysical fuzzball would remain almost indistinguishable from an ordinary Kerr black hole with every instrument we currently possess? A telescope cannot currently point at a dark object in space and tell us whether it is made from fuzzball microstates. That is worth saying immediately. We have observed objects whose masses, motions, accretion flows, and gravitational wave signals behave remarkably well, like the black holes predicted by general relativity. We have images of the environments around the compact objects at the centres of M87 and our own galaxy. We have detected gravitational waves from merging compact objects, whose signals agree very well with the behaviour expected from black holes. None of those observations has given us a little label reading, string theory microstructure detected. As of 2026, there is no accepted direct observational evidence that astrophysical black holes are fuzzballs. But that does not mean the idea rests on nothing. The evidence for fuzzballs is primarily theoretical, and it comes in several different forms. Some parts are quite strong within specific string theory systems, other parts are much more speculative. Keeping those categories separate is important, because otherwise a fascinating proposal can quickly turn into a claim that physicists have already solved the interior of every black hole in the sky. They have not. The strongest starting point is the microscopic entropy calculation we encountered earlier. Certain black holes in string theory have an entropy that can be calculated using the area of their classical horizon. The same entropy can also be reproduced by counting quantum states built from strings and branes. That agreement is difficult to dismiss as a coincidence. It tells us that, at least in those controlled examples, black hole entropy really can count identifiable microscopic states in string theory. The black hole is not simply assigned an entropy, because the equations happen to resemble thermodynamics. There are enough quantum states to account for the number. This was the first major clue. The next clue was more surprising. When physicists tried to describe individual states rather than merely count them, they found examples of horizonless configurations. Some of these microstate geometries look almost identical to the corresponding black hole geometry when viewed from far away. Travel inward, however, and they eventually differ. Instead of continuing through a conventional event horizon toward a singular interior, the geometry can cap off. Different states can cap off in different ways. Those examples provided concrete support for the possibility that the classical black hole is a coarse description of many microscopic states, rather than the exact geometry of each individual state. Reviews of the Fuzzball and microstate geometry programs emphasize both this progress and the substantial work still required to describe generic black holes. This is real mathematical evidence for the proposal, but we have to notice exactly what it proves. It proves that string theory contains important families of horizonless states carrying the same kinds of charges associated with particular black hole systems. It does not prove that every state contributing to the entropy of a realistic black hole has a simple smooth geometry, and it certainly does not prove that the rotating black holes produced when real stars collapse are described by the particular supersymmetric examples that theorists can calculate most easily. That gap between special examples and generic black holes is one of the largest unresolved problems in the Fuzzball program. The examples we understand best often have features that make the calculations unusually friendly. They may preserve supersymmetry. They may carry several carefully chosen charges. They may exist in 5-dimensional settings, or involve compact dimensions arranged in ways useful for string theory calculations. A black hole formed from a star in our universe does not arrive with a note saying, "For your convenience, I have preserved enough supersymmetry to simplify the algebra." Real astrophysical black holes are generally expected to be electrically neutral to a very good approximation. They rotate, they interact with messy environments, they form dynamically. A successful complete Fuzzball description would eventually need to explain objects much closer to those. Researchers have constructed increasingly rich microstate geometries, including families known as superstrata, and the mathematical landscape has grown far beyond the earliest two-charge examples. Nevertheless, even supporters of the program distinguish these successes from a complete construction of the full set of typical states of generic astrophysical black holes. The word typical is doing a great deal of work here. Suppose a black hole has an enormous number of possible microstates. Physicists might successfully construct several beautiful examples. Those examples tell us that such states can exist. But entropy is dominated by the overwhelming majority of states, not by the small number that happen to be easiest to write down. If the easy states have unusually high symmetry or unusually simple geometry, they might not resemble a typical member of the full quantum ensemble. This has led to criticism of the Fuzzball program. Suvrat Raju and Pushkal Srivastava, for example, argued that known two-charge Fuzzball geometries do not justify the claim that typical black hole microstates possess large, reliable classical deviations from the ordinary black hole geometry. They argued that typical state differences may become significant only extremely close to the horizon, where quantum fluctuations themselves make a simple classical geometry unreliable. They also raise problems with interpreting particular proposed geometries as representative black hole microstates. Supporters of the Fuzzball and microstate geometry programs disagree with several aspects of that interpretation. They argue that the growing collection of explicit states, duality relations, entropy calculations, horizonless solutions, and holographic descriptions points toward a genuine replacement of the traditional horizon and singularity picture at the microscopic level. That disagreement is useful to know about. There is no scientific requirement that a promising quantum gravity program arrive with unanimous applause. The actual question is whether future theoretical and observational work can distinguish the possibilities. Another major difficulty is formation. It is one thing to construct a Fuzzball state. It is another to start with an ordinary star and show precisely how that star becomes one. The conventional general relativity story is conceptually clear. A sufficiently massive object collapses, an event horizon forms. Matter continues inward. The external geometry settles toward a black hole solution. The Fuzzball story has to change that process before information becomes trapped behind a permanent classical horizon. One proposal is that the collapsing quantum state can spread into the enormous number of available Fuzzball microstates. A transition amplitude to any particular state may be tiny, while the total number of possible Fuzzball states is enormous. The huge degeneracy could therefore make the collective transition important. Interesting idea. extremely difficult calculation, a complete, realistic description of stellar collapse producing a generic fuzzball has not yet been achieved. That missing dynamical story is not a minor technical detail. If fuzzballs are supposed to replace astrophysical black holes, nature needs a way to make them. Then there is stability. A black hole can sit in space for an extremely long time. A fuzzball candidate representing one should also avoid immediately destroying itself through some uncontrolled instability. Individual horizonless compact objects can suffer instabilities that ordinary black holes avoid. Rotating horizonless objects, for example, can sometimes develop ergo-region instabilities. Trapped modes can also behave differently when there is no event horizon to absorb them. Some microstate geometries have shown encouraging stability properties under particular perturbations, while other configurations can possess long-lived trapped modes or potential instabilities. Numerical work on certain four-dimensional microstate geometries has found a prompt response resembling black hole ringdown followed later by echoes, while also finding evidence for linear stability in the example studied. Notice how useful that result is. The very features that create theoretical headaches can become observational opportunities. If a classical event horizon absorbs whatever falls through it, while a horizonless microstate geometry eventually reflects or reprocesses some disturbances, the two objects may respond differently after being perturbed. A black hole merger gives us a particularly violent way to perform that experiment. When two black holes merge in general relativity, the newly formed object settles down. The gravitational wave signal after the merger contains a stage called ringdown. The remnant behaves rather like a struck bell, although the bell in this case is curved space-time, and the ringing frequencies are determined mainly by the black hole's mass and spin. For a Kerr black hole, these characteristic damped oscillations are called quasi-normal modes. An object with structure near the would-be horizon could respond differently. The first part of the signal might still look almost identical. That happens because the early ringdown is strongly influenced by the region around the photon sphere, outside the horizon. A very compact horizonless object can possess an exterior almost indistinguishable from Kerr in that region. So the first ringing can fool you. Later, something interesting may happen. Part of the disturbance can travel inward, interact with the internal structure, and return outward. It can become trapped between the inner structure and the effective potential barrier farther out. Some of that energy may then leak back to infinity. The result could be a sequence of delayed features known as gravitational wave echoes. Certain explicit microstate geometries produce this kind of behavior in theoretical calculations. Echoes sound wonderfully convenient. Detect echo, announce fuzzball, go home early. Unfortunately, nature rarely organises experiments around our preferred press release. Many different exotic compact objects can produce echo-like behaviour. A detection would not automatically identify string theory. The detailed timing, frequency structure, damping, and response would have to agree with a specific physical model. There is also the less exciting problem that weak signals buried in detector noise can occasionally resemble almost anything if enough templates and statistical choices are tried. Several groups have searched gravitational wave data for echoes. Claims and counterclaims appeared after the first black hole merger detections. Larger analyses have generally not produced convincing evidence. A search using binary black hole events from the third LIG O Virgo Cagra observing run found results consistent with detector noise rather than significant echo signals. So there is currently no accepted gravitational wave echo detection demonstrating fuzzball structure. That may mean the structure is not there. It may mean its signal does not look like the simple echo templates used in searches. It may mean the effect is too weak, or the relevant observations may simply not yet be sensitive enough. Future detectors will improve the situation. Ground-based observatories will continue measuring stellar mass mergers, while planned space-based gravitational wave observatories offer a different opportunity. LISA, the Laser Interferometer Space Antenna, is designed to observe gravitational waves at much lower frequencies than ground-based detectors. One especially valuable type of source will be an extreme mass ratio in spiral. That mouthful is normally shortened to EMRI, which is considerably kinder. An EMRI occurs when a relatively small compact object, perhaps a stellar mass black hole, spends a long time orbiting a much more massive compact object before finally plunging inward. The small body can complete an enormous number of orbits in the strong gravitational field. Each orbit carries information about the geometry. Think of it as repeatedly tracing the shape of space-time with a very expensive pencil. A Kerr black hole has a tightly constrained set of multipole moments. Once its mass and spin are known, the higher multipoles follow a specific pattern. Some fuzzball and microstate geometries can possess additional or altered multipole moments, because their microscopic structure is less symmetric. An EMRI waveform may therefore reveal tiny departures from Kerr. Work published in 2026 specifically studied how LISA could constrain generic multipolar deformations motivated by fuzzball structure, and found that long EMRI observations could probe such deviations far more precisely than current measurements. That does not mean LISA is expected to discover fuzzballs. It means LISA could become a powerful test. There is an important difference. If LISA measures the Kerr multipole structure with extraordinary precision, large classes of horizon-scale alternatives could be constrained. If it finds consistent deviation, physicists would then need to determine whether the cause is a fuzzball, another exotic compact object, environmental effects, modified gravity, or some error in the model. Quantum gravity rarely provides only one suspect. Black hole imaging offers another possible route. The Event Horizon Telescope does not photograph the event horizon directly. It observes radiation from hot material around extremely compact objects at angular resolutions fine enough to reveal a dark central region surrounded by bright emission. The size and shape of that dark region are heavily influenced by strong gravitational lensing and the behavior of photons near the compact object. A sufficiently compact fuzzball can produce something that looks remarkably similar to a black hole shadow. Calculations of explicit horizonless fuzzball geometries have found that light can become trapped on complicated, highly redshifted trajectories near the would-be horizon. In sufficiently deep configurations, this can create a dark image closely resembling an ordinary black hole shadow. That result is both encouraging and annoying. Encouraging because fuzzballs can reproduce an important black hole-like observational feature. Annoying because reproducing the feature makes them harder to test. If the image looked completely different, one good telescope observation might settle the matter. Instead, some microstates can hide behind their own strong gravitational lensing. Possible differences could appear in details: residual light escaping from the central region, asymmetries, fine structure in photon rings, time-dependent brightness patterns, unusual lensing caused by non-Kerr multipoles. But astrophysical accretion flows are messy. Magnetic fields, plasma physics, turbulence, uncertain viewing angles, and changing emission can all affect the image. Distinguishing a tiny quantum gravity signal from ordinary hot gas doing something inconvenient is not easy. Surface emission provides another test in principle. If an object has a material surface rather than a horizon, matter falling onto it can hit the surface, heat it, and radiate. That fact has been used to constrain various horizonless alternatives to black holes. A fuzzball, however, is not a simple hard star with an ordinary surface. Its enormous redshift and its microscopic absorption and re-emission processes can make the observational story more complicated. Photons emitted near the would-be horizon can struggle to escape. Many trajectories return toward the object. Energy can become trapped for long periods. So the absence of obvious surface glow does not immediately rule out every fuzzball model. It does force any realistic model to explain the observed darkness. Tidal effects may also contain information. Place an object in an external gravitational field and it can deform. The response is characterized by quantities called tidal love numbers. For classical four-dimensional black holes in general relativity, the static love numbers have unusual properties, including vanishing values in the simplest cases. Horizonless objects can respond differently. Microstate geometries may therefore possess tidal signatures that distinguish them from Kerr black holes. Again, gravitational waves from Longin spirals are one of the most promising places to search for such differences. Then there are the multipoles we mentioned earlier. A perfect Kerr black hole has a remarkably economical gravitational fingerprint. Its entire sequence of mass and current multipole moments is fixed by mass and angular momentum. Some explicit fuzzball geometries are much less tidy. They can break axial or reflection symmetries and possess richer multipolar structures. Calculations have shown that these differences could provide observational targets, particularly for future EMRI measurements. We should be careful not to combine all these possibilities into one prediction. A fuzzball is not guaranteed to produce a loud echo, a strange shadow, a large tidal love number, and an obvious multipole anomaly at the same time. Different microstates can behave differently. A typical microstate may not resemble the smooth geometries we can currently calculate. Some observational effects may be dramatically suppressed by redshift. Others may average away. A realistic astrophysical ensemble could look much more like Kerr than one especially convenient theoretical example. That creates a difficult balance for the entire proposal. A successful fuzzball must differ enough from a classical black hole to preserve information. But from far away, it must resemble a classical black hole extremely well, because real compact objects already agree closely with general relativity. Too much difference and observations rule it out. Too little difference, and we have to explain how the microscopic structure solves the information problem. There is also the problem of timescale. A signal may technically carry information, but take an extraordinary amount of time to escape. A mode trapped deep inside a throat can remain there for a very long period as measured by a distant observer. That may make the object effectively indistinguishable from a black hole during any realistic observing campaign. Nature is allowed to hide the answer behind a signal that arrives after the telescope funding has expired. The observational challenge therefore becomes very specific. We are not looking merely for something strange near a black hole. We are looking for deviations predicted by a well-defined microstate model that cannot be reproduced more simply by ordinary astrophysics or another compact object theory. At present, no such observation has established that astrophysical black holes are fuzzballs. Echo searches have not produced an accepted detection. Current imaging can be mimicked by sufficiently compact horizonless microstate geometries, and the most precise proposed tests of fuzzball-inspired multipolar structure rely heavily on future gravitational wave measurements such as LISA EMREs. The theoretical situation is almost the reverse. There, fuzzballs have achieved results that observations have not yet tested. String theory successfully counts microstates for special black holes. Explicit horizonless configurations exist. Some reproduce the expected charges in asymptotic geometry. Some have radiation or dynamical properties that can be matched to microscopic descriptions. Large families of increasingly complicated solutions have been developed. At the same time, critics correctly force the program to answer hard questions about typicality, quantum fluctuations, realistic collapse, generic non-supersymmetric states, stability, and whether smooth microstate geometries represent the states that dominate black hole entropy. That leaves fuzzballs in an unusual scientific position. They are not merely a loose science fiction possibility. There is serious mathematical structure behind them. They are not experimentally established objects either. The black holes in our telescopes have not announced which microscopic theory they prefer. Perhaps future gravitational wave detectors will reveal departures from Kerr. Perhaps more precise images will expose structure where a horizon should be. Perhaps every measurement will continue agreeing with classical black holes so closely that broad classes of fuzzball models become increasingly constrained. And perhaps the exact microscopic states will remain almost impossible to distinguish directly, because the classical black hole is such an effective coarse-grained description. Whichever outcome nature chooses, the question has become much sharper than it was when black hole entropy was first discovered. We no longer need to ask only whether quantum gravity somehow changes a black hole. We can ask which degrees of freedom store its information, whether an exact state has a horizon, how its multipole moments differ from Kerr, how it rings after a merger, how light moves around it, and what kind of radiation it emits. Those are questions that connect the most abstract parts of string theory to actual measurements. And once we put all of these pieces together, the information paradox, strings, branes, microstates, horizon scale structure, infalling observers, and the possibility of observation, we can finally return to the question in the title without treating fuzzball as a strange word that needs an even stranger explanation. What we need now is a precise answer to what a fuzzball actually is, what it is not, and how much of the familiar black hole survives once the microscopic description is taken seriously. Strip away the equations, the extra dimensions, the D-branes, the long throats, the entropy formulas, and the arguments about Hawking radiation, and the fuzzball proposal makes one surprisingly direct claim. A black hole may not have an empty interior at all. What we normally call a black hole could instead be one specific quantum state, made from the degrees of freedom provided by string theory, with complicated structure extending across the region, where classical general relativity would have placed the horizon and interior. That is a fuzzball, not a ball of ordinary matter, not a small object hidden at the singularity, not a shell placed around an otherwise normal black hole, and not a conventional black hole with some strings floating inside it. The more radical idea is that the strings, branes, fluxes, topology, and other quantum degrees of freedom are the microscopic object. The familiar smooth black hole appears when we stop resolving those details. From sufficiently far away, a fuzzball can have the mass, charge, angular momentum, and gravitational field expected from the corresponding black hole. Move inward, and the microscopic description eventually stops agreeing with the traditional picture. Classical general relativity says there should be a smooth event horizon followed by an interior. The fuzzball proposal says the exact quantum state has structure instead. That one change reaches back through almost everything we've discussed. It changes where information is stored. It changes how radiation can carry information away. It changes what we mean by a horizon. It changes the status of the black hole interior. And, if the broad idea is correct, it may tell us something rather important about space-time itself. Start with information. A star collapses. In ordinary quantum mechanics, the quantum state describing that star contains information. The state can evolve. The information can become scrambled. It can become distributed among a huge number of degrees of freedom. It can become so difficult to reconstruct that no one in practice could ever do it. But the fundamental evolution should not simply delete it. The traditional black hole description creates trouble because the information crosses a smooth horizon, while Hawking radiation emerges in an almost thermal form. Eventually, the black hole can evaporate. If the radiation does not contain the information and nothing remains behind, the initial quantum state has apparently been erased. Fuzzballs change this because there is no information-free horizon in the exact microscopic description. The collapsing state becomes one of an enormous number of possible fuzzball states. Its details are represented by the microscopic configuration. Radiation comes from that quantum system rather than from a perfectly featureless vacuum horizon. Different states can therefore, in principle, emit radiation with different detailed correlations. To a simple detector, the radiation may still look almost thermal. That is important. A fuzzball does not solve the information problem by making black holes flash their contents into space like malfunctioning projectors. The information can be extraordinarily scrambled. Recovering it could require measurements of correlations among an immense number of particles. But the distinction between difficult to recover and fundamentally destroyed is the entire point. A complicated quantum object is allowed to scramble information. It is not allowed to erase it if the evolution is unitary. That gives us a useful first answer. A fuzzball is a proposed information-preserving microscopic description of a black hole in string theory. But that definition leaves out what may be the stranger part. The black hole interior itself may not be fundamental. Think carefully about what an interior means in the traditional picture. You cross the horizon. Space-time continues. There are locations deeper inside. Your future-directed path takes you toward the singularity. The interior is treated as part of the geometry, just as the region outside the black hole is part of the geometry. It seems perfectly natural to ask what objects are located there. Where is the matter? How close are you to the singularity? What direction can you travel? The fuzzball proposal asks whether those questions are being applied to a region that only exists in an approximate description. An individual fuzzball state can end before the conventional interior appears. The geometry can cap off. There may be no literal region corresponding to the smooth classical continuation through the horizon. If an effective interior emerges for certain high-energy processes, as fuzzball complementarity suggests, that interior would not necessarily be a separate hidden volume sitting permanently behind the fuzzball. It could be an approximate description of collective dynamics involving the microscopic degrees of freedom. This is a much bigger change than replacing one object with another. We are used to putting things inside space. A planet occupies space. A gas cloud occupies space. A cup occupies space, usually somewhere inconvenient once you turn the lights off. String theory and quantum gravity suggest that at a sufficiently fundamental level, this separation may fail. The quantum state and the geometry may not be independent ingredients. Change the state and you can change the space-time description. What we call space may partly emerge from relationships among more fundamental degrees of freedom. The fuzzball program does not by itself give us one complete theory explaining the emergence of all space-time, but it gives a sharp example of why physicists suspect the question has to be taken seriously. An enormous collection of black hole microstates can share essentially the same exterior geometry. The detailed states differ. Coarse grain over them, and the classical black hole can appear. Resolve the state, and the conventional horizon interior may disappear. Geometry, in that situation, depends on how much microscopic information you're keeping. We already accept something similar with thermodynamic quantities. Temperature is real. Put your hand near a hot oven, and you will not be comforted by someone explaining that temperature is emergent. But an individual molecule does not carry the temperature of the whole gas. Temperature becomes meaningful when we describe a large collection of microscopic particles statistically. Pressure works in a similar way. A single gas molecule does not possess the pressure of the room. Pressure emerges from collective behavior. The black hole interior could represent a far more surprising version of the same general lesson. It might be a useful, large-scale description that emerges when we stop keeping track of the exact microstate. Useful does not mean fake. Emergent phenomena can be completely real at the level where they apply. A wave in the ocean is real even though the individual water molecules are not little waves. A sound wave is real even though an individual molecule of air is not humming the melody on its own. If an effective black hole interior emerges from collective quantum behavior, an observer could potentially use that description successfully under the right conditions without the interior being fundamental in the microscopic theory. This is why the disagreement between general relativity and fuzzballs does not necessarily mean Einstein's theory is simply wrong. General relativity can remain an extraordinarily accurate large-scale theory. The question is whether its continuation through the horizon is still describing the exact microscopic state. Far outside the black hole, there is little reason for the distinction to matter. The total mass dominates. The total angular momentum matters. Ordinary gravitational predictions work. Only when we ask extremely fine questions about information, entanglement, horizons, and the interior does the microscopic structure become unavoidable. This pattern appears throughout physics. Newton's laws are not useless because relativity exists. They remain excellent when speeds are low compared with the speed of light, and gravitational fields are not extreme. Classical mechanics is not useless because quantum mechanics exists. You do not calculate the wave function of every atom in a bicycle before riding it. A theory can be an extremely accurate approximation without being the final microscopic description. The Fuzzball proposal suggests that the classical black hole may be exactly that kind of approximation. Very good from the outside, very useful for many calculations, potentially misleading when treated as the exact quantum state. There is another clue pointing in the same direction. Black hole entropy depends on area. That remains one of the strangest features of the entire subject. For ordinary systems, we often expect the number of degrees of freedom to grow with volume. A larger box can hold more particles. More volume gives you more places to arrange things. A black hole's entropy instead scales with the area of its horizon. That observation helped motivate the holographic principle, the broader idea that gravitational systems may sometimes be completely described using degrees of freedom associated with fewer dimensions than the bulk spacetime seems to contain. String theory gave one of the most powerful realizations of this idea through gauge/gravity duality. In examples such as the ADS/CFT correspondence, a gravitational theory in a higher dimensional spacetime can be equivalent to a quantum theory, without gravity living in fewer dimensions. A black hole in the gravitational description corresponds to an ordinary quantum state, or thermal ensemble in the dual theory. From the viewpoint of the dual quantum system, information is not supposed to disappear. That has provided some of the strongest reasons physicists now expect black hole evaporation in a complete quantum gravity description to preserve information. Fuzzballs approach the same issue from the microscopic gravitational side. Instead of relying only on a dual quantum theory to assure us that information must survive somehow, the program tries to identify the actual string theory states that replace the featureless black hole. The two perspectives are not identical, but they are connected by the broader lesson that classical geometry does not contain the full microscopic story. Then there is the singularity. For decades, the traditional black hole picture seemed to force everything toward a place where general relativity breaks down. Classical curvature becomes unbounded. Ordinary space-time description fails. Many physicists have long expected that a quantum theory of gravity must remove or reinterpret singularities. The Fuzzball picture offers a particularly strong version of that possibility. The theory does not wait until matter reaches an infinitely small central region and then repair the equations at the last moment. The microscopic state can alter the geometry before a conventional horizon and singular interior ever form. The singularity disappears because the space-time that contained it was never the exact microstate. This is an attractive feature. It is also one of the proposal's largest commitments. Replacing the singularity is relatively easy to motivate. Most physicists already expect something new, where classical gravity produces infinities. Replacing the smooth horizon is far more controversial. Nothing locally pathological needs to happen at the horizon of a large classical black hole. The curvature can be weak. The equivalence principle suggests a freely falling observer should notice nothing special. Why would string-scale quantum physics reorganize the state across such a large region? The answer offered by the Fuzzball program comes back to entropy and information. A black hole is not just one classical geometry, it represents an exponential number of quantum states. The enormous phase space of those states can make quantum effects important in ways that would not be obvious from local curvature alone. The scale of quantum behavior is then controlled not only by how curved space-time is, but also by how many microscopic states are available. Whether this reasoning can be developed into a complete description of generic astrophysical collapse remains one of the major open questions. And that brings us to what fuzzballs do not currently tell us. They do not give us a complete microscopic model of every black hole we observe. They do not tell us the exact fuzzball state of Sagittarius, a star. They do not yet provide a universally accepted calculation of a normal massive star collapsing into a realistic rotating fuzzball. They do not establish exactly what every possible infalling observer experiences. They do not prove that all black hole microstates can be represented by smooth horizonless geometries, and they have not been experimentally detected. Those limitations are important because the phrase, "fuzzballs solve the information paradox," can sound more definitive than the current situation warrants. The program provides a mechanism that can solve the paradox if the required picture of black hole microstates is correct. It has strong support from particular string theory constructions. It reproduces black hole entropy in important cases. It provides explicit horizonless microstate geometries. It gives examples of state-dependent radiation. It offers a reason information need never disappear behind an information-free horizon. Those are substantial accomplishments. Turning that framework into a complete description of realistic black holes is another task. There are also competing and complementary ideas in modern black hole research. Holographic approaches involving quantum extremal surfaces and islands have made major progress in reproducing the Page curve for evaporating black holes. Those calculations show how a gravitational description can produce the entropy behavior expected from unitary evaporation. They have strengthened confidence that information is preserved, but they also raise their own questions about how the microscopic information is encoded and exactly what happens to the traditional interior. Fuzzballs approach those questions through explicit stringy microstructure. Other programs emphasize holographic encoding, space-time entanglement, or different descriptions of the black hole degrees of freedom. A complete theory may eventually reveal that some ideas currently discussed as separate are different limits or descriptions of the same underlying physics. String theory has done that before. It spent years presenting physicists with several apparently different theories before dualities revealed that they were deeply connected. Quantum gravity may have a similar sense of humour. What fuzzballs already make difficult to maintain is the naive picture of a black hole as simply an empty region with all the information crushed into an unknowable central point. Black hole entropy tells us there are microscopic degrees of freedom. Quantum mechanics tells us information must be accounted for. String theory shows that those degrees of freedom can exist in explicit systems. Microstate geometries show that some individual states can differ radically from the classical interior. Whether every detail of the fuzzball proposal survives future work or not, the old picture has become much harder to regard as the complete answer. There is another consequence that reaches beyond black holes. If space-time can emerge from quantum degrees of freedom, then empty space may not be truly empty in the fundamental theory. We normally think of emptiness as what remains after all the particles have been removed. Take away the atoms, take away the photons, take away the dust, you're left with space-time itself. Quantum field theory already complicates that intuition, because the vacuum is a quantum state of fields, not a literal absence of everything. Quantum gravity pushes the question further. Perhaps space-time is not the container left behind after the contents are removed. Perhaps space-time itself comes from underlying quantum relationships. In that case, asking what lies inside a black hole may resemble asking what lies beneath the surface of a computer image while refusing to discuss the pixels and the electronics producing it. The geometric description is valid at one level. At a deeper level, different variables may be doing the work. That does not mean the universe is a simulation. It does not mean space is fake. It means our everyday categories may not be fundamental. Physics has given us that lesson many times. Solid objects turned out to be made from atoms. Atoms turned out to contain nuclei and electrons. Nuclei contain protons and neutrons. Protons and neutrons contain quarks and gluons. Particles themselves are described through quantum fields. String theory asks whether even that description is part of a deeper structure. Black holes force the issue because they place quantum mechanics and space-time in direct conflict. A fuzzball is therefore more than an unusual alternative object. It is a test of what we mean by an object in quantum gravity. Is a black hole a region of space-time? Is it an enormous quantum state? Is it an ensemble of microscopic configurations? Is the smooth geometry an average? Can an interior emerge only for certain observers and energies? Those questions sound philosophical until the equations force us to answer them. The information paradox did exactly that. Hawking's calculation took a seemingly simple question about radiation and exposed a disagreement about the basic structure of reality. If information is preserved, then something about the traditional black hole description cannot be exact. Fuzzballs make one specific choice: keep quantum mechanics, keep information, keep the successful exterior predictions of gravity, change the horizon and interior at the microscopic level. That is the bargain. Whether nature accepts it is still unknown. Future observations may help. More precise gravitational wave measurements could test the multipole structure of compact objects. Long-in spirals could probe deviations from Kerr. Ring-down measurements could search for unexpected structure. Black hole imaging may constrain unusual behavior close to the photon region. Perhaps every result will continue agreeing with classical Kerr black holes. Even then, the microscopic question would remain, because a fuzzball or another quantum gravity state might imitate Kerr extraordinarily well at observable scales. Or perhaps some small discrepancy will survive every conventional explanation. That would not immediately prove string theory. Physicists would first have to eliminate less exciting possibilities, which is one of science's less glamorous but more reliable habits. A strange gravitational wave feature does not automatically mean extra dimensions. Sometimes the detector was having a difficult Tuesday. For now, fuzzballs remain a theoretical proposal, supported most strongly by the internal evidence of string theory, and by the demand that black hole evolution respect quantum mechanics. They give us a concrete way to imagine how an object can look like a black hole without containing the classical black hole interior as a fundamental region. And after everything we've covered, the name itself now seems almost misleadingly simple. A fuzzball is not really defined by fuzziness, it is defined by microstructure. One black hole mass can correspond to an enormous number of possible quantum states. Each state contains information. The state can extend across the would-be black hole region. The ordinary horizon is replaced by structure. The singularity need not appear. Radiation can depend on the microstate. The classical geometry becomes an effective large-scale description rather than the complete microscopic object. That is what a fuzzball is, really. Or, more carefully, that is what the fuzzball proposal says a black hole may really be. And perhaps that final word, may, is the most important one. We do not yet know whether astrophysical black holes are fuzzballs. We do know that black holes have forced physics into territory where our two greatest descriptions of nature, quantum mechanics and general relativity, cannot both be applied in their simplest forms. Something deeper has to connect them. String theory offers one possibility. Fuzzballs are one of the strangest consequences of taking that possibility seriously. So if you picture a black hole tonight, perhaps don't imagine only the familiar dark sphere with a point hidden somewhere in the middle. Imagine instead that the simple exterior might be concealing an enormous quantum state, not concealed behind the horizon, concealed by our coarse description of what we are looking at. From far enough away, all those microscopic possibilities can look like one simple object. Move closer in the theory, and the simplicity disappears. Strings can wrap, brains can bind, momentum can move through compact dimensions, quantum states multiply, geometry can cap off, information can remain part of the system, and the empty interior we thought was unavoidable may turn out to have been an approximation, which leaves us in a curious position. We began with something called a fuzzball, a name that sounds almost deliberately harmless. We ended up asking whether space itself is fundamental. Black holes have a habit of doing that. You ask what happens to a falling object and discover a problem with quantum information. You ask where the information is stored and discover black hole entropy. You ask what the entropy counts and find strings and brains. You ask what those microstates look like, and the horizon begins to disappear. Then you ask what remains, and suddenly the thing under investigation is not just the black hole anymore. It is space-time. And if you've stayed with me through all those strings, brains, paradoxes, horizons, microstates, and one surprisingly persistent ball of fuzz, I'd be curious to know where you're listening from tonight. Perhaps also tell me what you imagined a fuzzball was before we started. A cosmic dust bunny is a perfectly respectable answer. If you found this journey soothing, interesting, or simply strange enough to keep your thoughts away from tomorrow for a while, you can leave a like and subscribe to Science for Sleep. It helps this quiet corner of science reach other people who might enjoy letting the universe become slightly more complicated before bedtime. There is still a great deal we do not understand about black holes. We do not know the final microscopic theory describing the ones scattered throughout our universe. We do not know whether an astronaut approaching one would meet fuzzball structure, an effective smooth horizon, or something our current language has not learned how to describe properly. But the information paradox has already taught us something useful. A black hole cannot be understood only by asking how strongly it pulls. We also have to ask what quantum state it is in, how many states are possible, where information lives, and whether the space-time geometry we draw is fundamental or only what those deeper degrees of freedom look like from far away. For now, that is where the fuzzball leaves us. Not with a photograph of what sits inside a black hole, but with the possibility that there was never an ordinary inside there to photograph in the first place. And somewhere beyond that question is whatever quantum description finally explains why gravity, information, space, and time fit together at all. Until then, your pillow remains considerably easier to understand than a black hole. Probably. Sleep well, fellow traveller.